you feel lost, you fade away. The feeling is so just another line, smile, the color of my blood. You're the truth, you're the only thing on the touch. So much, so much. I should like my piano. Let me know. Calm down, calm down. Yo, this your body, put it right. Hold up down, hold up down, hold up down. Yo, you feel like Fantown, Fantown. If I tell you say I love you, you know they from a young girl. No young girl, no tell me no, 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 whoa, 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 whoa. Baby girl, baby girl, you feel like, girl, if I know, I might think she right, hello. We are the girl that they should do, but she's coming. Hey, my divine, and I go use section, I'm hello. Suddenly, I want to go to the game, but she off, hello. You're gonna go, oh, you know I'm going for making me so small, and I know she wasn't know. She didn't think, oh, it's a business. One like you, oh, when they come like you, oh, I'm sorry. This is a big thing. Sorry.
Good morning. I thought that was a thing to keep it from sliding off, but it doesn't. Good morning, all, at the focus meeting at this General Assembly on History of Astronomy in South Africa and the late modern period. My name is Piet van der Kruis from the Netherlands, from the Kaptein Astronomical Institute. I am the chair of the Scientific Organizing Committee, but that doesn't really mean that I should have be given any credit for this meeting. It's all been organized, uh, conceived, worked out, and all the work is done really by Chris Sterken, the president of IAU Commission C3 on the history of astronomy. So if there's any credit, it goes to him. So very welcome today. We have a very interesting program, I think, and it is my duty to introduce the meeting very briefly. I'll do that actually by quoting from the lines that Chris wrote when he organized this meeting and the purpose of it. Describing the content of various astronomical archives that currently hold photographic plates collected in South Africa since the application of photography in astronomy, describing the associated documents in these collections, such as logbooks, brands, and types of photographic bulletin, and observing rosters, safeguarding and conservation of above-mentioned archives, as well as the protection and preservation of geodetic survey records, maps, and plans. I think this is a very fitting subject, and I think it was an excellent initiative of Chris to propose this meeting and to work out all the details and put the program together. I should recall there is one very sad occasion, and that is that Virginia Trimble will not be here. She is not in very good shape, and I think we will miss her sorely. But I certainly feel that the credit, to give her the credit for so much work she's done, not for astronomy in general, but in particular for the history of astronomy, to give her a special mention in this introduction. So we hope she gets better, but things are looking rather serious. So the first session is Cape Observatory Astrophotography. We have three contributions, and two of them are invited and left half an hour. One is a contributed paper for 20 minutes. We have to include some time for discussion, so what I'll do, I'll give people a warning 10 minutes before the end, so they have about 5 minutes to wrap up. Give them a second warning 5 minutes before the end of that time. So if the speakers then wrap up, we have some time for discussion. So I hope you enjoy the meeting. It certainly is it's a very interesting program. I think it will be very interesting to listen to all these important contributions by people that know so much about all these subjects. So the first contribution is by John Hernshaw. It's called The Fascinating Story of the Cape Photographic Doormoesterung, involving the different personalities of David Gill and Jacobus Kaptein. John, you have the floor. So that's this one, that's first one.
And this works, does it? Okay, good. Okay, thank you very much, Pete, for the introduction. I'm going to talk about the Cape Photographic Durchmusterung and the work of David Gill and Jacobus Kaptein, which was undertaken in the late 19th century. So I press the button and okay, this one works. So let's go back to the 1880s and consider the state of astronomy at that time. And photography was just coming in as a tool for astronomers. And there was tremendous optimism at this time that the new dry photographic plates, gelatin on glass, were going to bring undreamed of advances in astronomy. And I think that was correct. Great advances were made when astronomers started using photography in a big way, but there are huge problems which were not anticipated, and especially problems for measuring stellar magnitudes. So photographic photometry was not as easy as people thought it would be, but when it came to just cataloging the positions of stars, then certainly photography was a great technique. And astronomers used photography for almost exactly 100 years. So from about 1880 to 1980, and then electronic solid state detectors such as the CCD came in. I mean, that's a great simplification, but essentially 100 years of photography started in around 1880. So let's go to Sir David Gill, Scottish astronomer who came to the Royal Observatory at the Cape of Good Hope as director in 1879, trained in Aberdeen, and for several years he had a job at a private observatory in Scotland. And that was Lord Lindsay's, the Earl of Crawford's observatory at a place called Dunecht. And he was an astronomer there for several years in the early 1970s. During that time, he went to Mauritius to observe the transit of Venus in 1874. But then 1879, he came here to Cape Town and served for several decades as director of the Royal Observatory. So here is David Gill sitting in a nice chair in the garden, probably at what is now SAAO. And there is a very old photograph. And by the way, some of these images I took from Piet van der Kruit's biography of Kaptein, Jacobus Kaptein. And I think that picture's in your book, is it, Pete? And that's probably the oldest photograph of an observatory anywhere in the world, taken in 1842. And that is the Royal Observatory was founded in 1820, the oldest scientific institution in Africa, as it happens, and still going strong. And that building is still there, as it was in 1842. So in 1882, there was a bright comet in the southern sky, and there was a amateur astronomer and photographer, professional photographer in Cape Town called E.H. Alice. And he was able to use photography to record this comet of 1882. And the top image there is Alice's photograph using a 2.5-inch f4.4 lens. And well, the comet looks very nice, but what is striking is the images of stars as well. And David Gill was very impressed with these photographs. So he tried photographing the comet himself, and the lower image is taken by Gill on the 7th of November of that year. And then Gill went to Paris for an Académie de Sciences meeting and met the director of the Paris Observatory, Ernest Mouchet. And Mouchet was very impressed with the ability of photography to record star images. So by late November 1882, about the same time, Gill resolved that he's going to make photograph the whole of the southern sky and do a survey comparable to what Argelander had done in Bonn, but visually, he's going to extend the Bonadurchmusterung into the southern hemisphere. So the Bonadurchmusterung went to about minus 18 degrees declination, and Gill decided he would extend the survey photographically from minus 18 to the South Pole. So he ordered a lens from John Dallmeyer, a famous optician in England, and that lens arrived. It's a 6-inch f9 lens. Gill mounted it in an astrograph, which you see there in this image, and it took large photographic plates. Gill got a grant of £300 from the Royal Society in 1885 to employ Ray Woods and to do this photographic survey. So this is the origin of the Cape photographic Durchmusterung, and observations began in April of 1885. The plates were quite large, 14 centimeters by 14 centimeters, roughly 6 inches square and covering 6 by 6 degrees. So the exposures were long, nevertheless, half an hour to 1 hour in that range. And Gill wanted to reach photographic magnitude 9.2, which is comparable to the Bonn limiting magnitude. I think that was 9.5. So he did 3,000 exposures over the next 6.5 years, and half of those were used for the Cape photographic Durchmusterung. And all these images, they overlap by about 1 degree, so the coverage was complete. And this just shows some of the fields between minus 18 and the South Pole, showing these overlapping fields, at least some of them. The next problem was how could Gill measure the positions and magnitudes of a large number of stars on those plates. He had Royal Society grants in 1885, as I mentioned, another one in 1886, but the Royal Society declined to fund Gill after that. And fortunately, Gill was in correspondence with Kapteyn, perhaps not explicitly to reduce these plates initially, but Kapteyn came up with a very generous offer. And Kapteyn wrote in December 1885, "I would gladly give up some years of my life to this work, which would disburden you a little, as I hope, and by which I would gain the honor of associating my name with one of the greatest undertakings of our time." Well, that's rather flowery 19th century language, and it certainly did relieve Gill very much of the burden of reducing all those plates himself. And so Gill started shipping the plates to the Netherlands, to Groningen, and Kapteyn was then undertook to measure star positions and magnitudes. Well, Kapteyn estimated 6 or 7 years of his life in the end, like all big projects, they take longer than you expect, and it took 13. Nevertheless, he devoted his time and of an assistant to these reductions, and one of the great catalogues of astronomy, the CPD, was the result. So here is Jacobus Kapteyn, and this was one of the most fruitful collaborations in the early history of astrophysics, and involving two institutions as equal partners in different countries and different continents indeed. And it was highly successful. So how did Kapteyn measure the plates? Well, first of all, he employed an assistant to do it. They devised an ingenious method. Rather than measuring XY coordinates of every star image on every plate, he had this so-called parallactic method with a small theodolite telescope pointing at the plates at a distance of 137 centimeters, which is the focal length of the astrograph. And you can measure the angle of the theodolite telescope offset using setting circles. So the observer looked through the eyepiece and offset the theodolite telescope and just measured the angle. And from that, directly right ascension and declination could be read. So it's a very ingenious and simple method. Probably any distortion in the plates gave small systematic errors, but the precision, the random errors, were relatively small. So Kapteyn employed this guy, T.W. de Vries. He was a teenager when he first started this work, and he spent his whole life at Groningen working there as an assistant. But his first big job was measuring all these plates. And it took a long time because there are far more stars in the southern hemisphere than expected, because the center of the Milky Way is in the southern hemisphere. So I told you how he measured the right ascension and declination. The magnitudes he came from the image diameters, and he used this interpolation formula where B and C are constants, different constants for every plate, because it would depend on focus and temperature and so on. So B and C were measured using stars of known magnitude to calibrate. So stars of known magnitude came particularly from Benjamin Gould's Uranometria Argentina, and Solomon Bailey at Harvard College Observatory had photographic magnitudes, but the Gould's magnitudes were done visually in yellow light. And of course, the CPD using photographic plates used blue and ultraviolet light. And by today's standards, it's extraordinary. If you think you can measure visual magnitudes with photographic plates in the blue and ultraviolet, would be crazy, because these plates were completely unfiltered. And of course, there were huge systematic errors. If you calibrate plates with visual magnitudes, estimated through an eyepiece, and expect to get a good correlation with the image diameters. So the random errors in the magnitudes were maybe a tenth of a magnitude or less, but the systematic errors were huge, especially for blue stars. Systematic errors could be half to one magnitude or even more in some cases. So these reductions took place from 1886 to 1892, and eventually the Cape Photographic Durchmusterung was published in 3 volumes with nearly 500,000 stars, quite a lot more than Argelander had for the Bonner Durchmusterung, where 329,000 stars down to -2 degrees, and Schoenfeld extended it to -18. So in a smaller area of sky, there were more stars in the southern hemisphere. And that's why it took quite a bit longer than expected. Well, after the publication of the 3rd volume of the CPD in 1900, Gill wrote, probably no work of the kind of like extent has ever been issued so free from typographical and other errors, it is impossible to overestimate its value to southern sidereal astronomy, and still more impossible to adequately express the gratitude which is due to Kapteyn for his self-sacrificing labors. Certainly, the CPD was published relatively quickly. By 1900, the whole thing was done, and it was very free from typographical errors. So here is just an example of what the volumes look like. Volume 1 is on the left. I think it's volume 3 is the one looking at the spine in the middle. And then a typical page, I think that's volume 2. So you see these various columns, and there are 4 columns there. Each column's got four parts. It's the magnitude, then the right ascension, then the declination, and then any references to that star in other catalogues of the time. So this was the first complete survey of the southern hemisphere to magnitude 9.2. For the first time, astronomers really knew what stars were present in the southern hemisphere. So this is probably my most important slide. Why was the CPD so revolutionary? The first complete survey of the southern sky to faint magnitude limits. It was the first ever international collaboration between scientific partners in different countries on different continents, and one of the first applications of astronomical photography for charting the heavens. Certainly not the only one. Paris with the Carte du Ciel, and Harvard College Observatory with Edward Pickering and Potsdam Astrophysical Observatory were very active in photography, but this is probably the first to produce really successful results. So in spite of all the systematic errors, these were great achievements. So that's the importance of the CPD. So Pickering at Harvard was also very active in measuring magnitudes photographically. And of course, the concurrent Carte du Ciel program aimed to photograph the whole sky to magnitude 11 using 33 centimeter astrographs at 20 participating observatories. And perhaps it was a tactical error that Gill would be so supportive of the Carte du Ciel, because he gave a lot of support to that program, as Ileana is going to talk about next, I think. And as a result, the Royal Society in London declined to fund Gill for the Cape Photographic Durchmusterung after the first 2 grants in 85 and 86. So Gill's active support for the Carte du Ciel cut off his funding for the CPD, but thank job done. So I'm not going to say much about Carte du Ciel because that's coming up with Ileana and other talks, but it was directed by Ernest Mouchet and the Henry brothers, and it took 75 years to complete the astrographic catalogue from the Carte du Ciel, and the actual map of the sky was never really properly completed, even after 75 years. Not all the plates were even taken. And in hindsight, Pickering in 1914, who never supported this project at all, it's interesting to quote what Pickering said about the Carte du Ciel: the great work of a chart of the entire sky, undertaken by the Paris Observatory in cooperation with several others, is a sad example of the danger of undertaking a work on too large a scale. It is predicted that at least 50 years must elapse before it is completed. In fact, it was longer than that. And no positions of any southern stars have yet been published. In striking contrast to this is the early completion of the Cape Photographic Durchmusterung, which gives the magnitude and positions of nearly 500,000 stars south of -19. So a big contrast between the success of CPD, in spite of the systematic errors, and the chaotic progress of the Carte du Ciel. How much time do I have? Oh, that's all right. There was another survey of the southern sky taken concurrently with the CPD, and that's the Cordoba Durchmusterung. And this, like Argelander and Schoenfeld in Bonn, was done visually. And it's the Cordoba of John Combe, the director of the Cordoba Observatory, and later extended. Combe went to minus 62, and he died in 1908. And then Chaudet and Thretter extended it to the South Pole, and it was published in 1932. So long after the CPD, the Cordoba Durchmusterung came out, and it went to magnitude 10.5, so over 500,000 stars, whereas the Cape survey had 500 and had just under 500,000. And the magnitudes were less precise because they're estimated visually, plus or minus 0.2 magnitudes. And also with large systematic errors. So the question of the errors and the magnitudes, Jakob Halm was a German astronomer at the Royal Observatory here at the Cape, and he analyzed the CPD magnitudes in 1907, and he concluded that in some cases they're even 2 magnitudes out, systematic error for the very blue stars at the faint end. And that was partly because the Milky Way has a lot of blue stars, and at minus 45 degrees, there are a lot of Milky Way blue stars at some right ascensions. So the errors were fairly extreme. Jakob Halm is in the middle of the back row in that image. Then Pickering was very active in photographic magnitudes, and he was actually more enterprising than Gill or Kapteyn in how to use photography to measure magnitudes. And he used trailed images and extrafocal images of stars to estimate magnitudes. And one of the problems of photography is plates saturate very quickly, but if you spread the light, put the astrograph out of focus, you can get a more accurate measure of magnitude from the density of an extrafocal image. So he came to similar conclusions to Halm, that there were large systematic errors. The scales were close at magnitude 6, but diverged greatly thereafter for the fainter stars by up to 1.7 magnitudes, according to Pickering. So that meant the magnitudes were perhaps of limited use and probably they're not referred to today at all. By the way, Pickering was one of those who introduced the Pogson scale into photographic magnitudes. And he said that one magnitude is 10 to the power 0.4, 2.516 times. And I'm not sure if Kapteyn did that because he was using these visual calibrations, which had not yet used the Pogson scale that we use today. So that's all I wanted to say about the CPD. It was a very revolutionary program. And there is Kapteyn and David Gill once again. Thank you.
Actually, met each other in person once the work began. Correspondence.
I am not sure of the answer, but Pete will know.
Remembered by his daughter, brother's biography from better now? So, well, oh, yeah, that's better. Gill visited Groningen a number of times, 3 or 4 times, if I remember well, in the course of his life. And Kapteyn actually visited Cape once, but that was after the completion of the CPD. But during the CPD, I think there was 1 or 2 meetings they had. They became very good friends, and after Gill returned to London, where he spent his final years, they visited a number of times. The Kapteyns visited London a number of times. So they've seen each other regularly and have corresponded, of course, extensively.
Thank you, Pete. I knew you should have been giving this talk all along. You're a real expert, but that what I do know is they corresponded a lot, and their letters, some of which I quoted from, are still extant. So that was a great friendship built on correspondence. Of course, in those days, when you wrote a letter, you put it in the mail. A month later, it might be received, and the answer would come 2 months after that. So, more questions. So we go to Sarah first, and then you.
My question is, when do they start to use color filtering for light? Thank you. My question is, when did they start to use colored filters with the photographic process, at least on the darkroom side, to try to correct for different wavelengths of light in the exposures?
Why? I think that was in the 1920s, and people didn't really think about the spectra of stars and wavelengths and colors very much before that. But the whole business of the North Polar sequence as calibration for photometry, it really required filters, and they were not used until the late 1920s, if I remember correctly. And that's why photometry had such a rocky start in life. And the CPD just came too early. So colored filters are really essential for anyone doing photographic photometry.
You have another question?
I just want to comment that Gill had a lot of opposition from the Astronomer Royal in England, and people feel he was actually jealous of what Gill was achieving. But one of the problems was that he didn't have enough money to start the CPD, so he suggested to his wife she spend half of his salary towards it. So she agreed, and it cost him a great many domestic economies, as he put it. But anyway, it was an important contribution to the funding.
Thank you, Ian. Yeah, it's very magnanimous of Gill's wife to do that. And so that must have caused quite a lot of privations in the Gill household, seeing half their salary disappeared to science.
I was intrigued by the way that Kapteyn set up essentially would set up the plate and then the theodolite and get right ascension and declination without having to do all the math, essentially right from the plate rather than. Takes a lot of that's right. It takes a lot of calculation.
Without a computer, it would have been a horrendous job. Probably more precise in the end, but not really realistic if you want to measure 500,000 stars.
Kapteyn, of course, developed that method himself, and he actually tried very hard to get the Cartier to adopt the same method. He even had some funding to build a prototype for it, but it was never adopted by the Cartier. So, when the Hipparcos satellite went up, they had to still reduce all the rectangular measurements to coordinates in the sky. Very clever. Yeah. Question I had, John, you had your title, The Different Personalities. So what can you say about the different personalities of Gill and Kapteyn?
Well, I think Gill was, I'm guessing a little bit, I think he was very ambitious and probably fairly extroverted, and Kapteyn was very methodical and careful operator probably a little bit introverted. Is that your assessment too? So they did have different personalities, but they seemed to collaborate extremely well.
They were
Complementary, exactly. So maybe that's a good thing, therefore. Yeah, two extroverts working together quite often doesn't work, as we've seen in American politics. Trump and Vance. Yes.
How did the two of them actually encounter each other in the first place? Where would they have first met? How would Captain have known about this work to make the volunteer?
They were corresponding, is that right? And
Kaptein had written a paper on determining absolute declinations, and he sent a copy of that to Gil, who read the paper. It was in German, actually. Gil said, "Oh, that's an excellent paper," and a few months later thought, "I had it translated. Now I can see it's an excellent paper." So maybe the first remark shouldn't be taken that seriously. And from then on, they kept agreeing. And Gil was mentioning all the time that he had so much work to do to get these things reduced as a sort of a bait to Kaptein, which took a half a year or so before Kaptein to take the bait.
Unfortunately, Captain seemed to be able to write English very fluently, like most Europeans, and Gil, being British, was hopeless at foreign languages. And of course, Captain was famous for his plan of selected areas in, I think, 1902. So 1906. All right, thank you. And so he had all these selected areas in the sky where he meant to get data for every kind of possible data for the stars in that area to do stellar statistics. So that was his next big project as soon as CPD had finished.
I think we have to move on in view of the time. So I'd like to call on the second speaker, Ileana Kinichi, I think is her pronunciation, the Cartichel project and the crucial role played by the Cape Observatory.
Which one? Which one? This one or this one?
Okay.
Thank you very much. As we have just listened from John, the Paris Observatory was one of the first astronomical observatory that has a photographic department. It was made thanks to the initiative of the director, Admiral Ernest Mouchet, who in 1879 established an atelier photographique at the observatory, and he entrusted this atelier to two famous opticians, the brothers Paul and Prosper Henry, and he charged them with the task to develop special photographic equipment for astronomical purposes. In 1882, Admiral Mouchet received a photograph already mentioned. This photograph was reproducing a picture of the comet of the Great Comet of 1882. This photograph came from Cape Observatory and was sent by the director, David Gale. But it was not interesting the subject of the photograph, but the background of the photograph. Sometimes like a sort of gestalt procedure. It was much more interesting the background, because the background was showing a number of stars, also faint stars. And this immediately drew the attention of the astronomers. As it has been already said by John, this photograph was sent by Admiral Mouchet was presented by Admiral Mouchet to the Académie des Sciences. And this report, in this report, Admiral Mouchet said that we are ready to have now, it is possible now, to make star charting by means of photographs. And of course, he charged the brothers Henry to develop this kind of equipment. And in 1884, they were able to obtain excellent plates, photographic plates of the sky. These plates were also sent to the Cape of because Gill was informed about these beautiful plates from, it was informed by Huggins. And he wrote to Mouchet that he was interested to have a copy and how have you obtained these results. And from this interest, a close correspondence started. And he also spoke to Mouchet about his idea, his project of make a photographic map of southern events. And Mouchet replied to Gill that he sent the photographs and explained all the details about these photographs. And also he announced that it was they were making a new special equipment for the photography, for star photography. And in May 1885, he announced to Gill that this instrument was ready. And this instrument was the Casirial photographique, a special astrograph made. The optical parts were by the Henry brothers, and the mechanical parts from the Paul Gaultier, an instrument maker in Paris. It was a double telescope with visual lens and photographic lens. And with this beautiful instrument, the brothers Henry were able to obtain wonderful plates with stars to magnitude 14. And of course, these plates were sent to Gill, and Gill was very impressed by these results. But it also wrote to Gill that yes, these are very interesting plates, but I don't think that star charts are really interesting from a scientific point of view. I think that it is much more interesting to have a catalog, star catalog. And of course, he didn't want to underestimate the value of the efforts of Mouchet, but he was much more convinced that catalog was much more important than a chart. In any case, he was ready to propose a plan for this photographic project, and also he said that the work should be undertaken on a carefully prepared plan, be continued on a uniform system, and only in a great national establishment we can find all these conditions. Anyway, he wrote that he was ready to cooperate for a carte du ciel project. Starting from this moment, the role of Gill in the project became more and more important for many reasons. First, because he really contributed to the planning of this project. Also because he gave many practical suggestions, provided many practical suggestions, but also he also tried to solve many problems. We can say that it can be considered like a sort of eminence grise of the project. And as we shall see, all the project was developed along the Paris Cape Town. First, the letter, a very important letter sent by Gil to Moshe in May 1886, contains a sort of draft of the plan of the project, and he suggested that this project to photograph the whole sky can be divided into two classes. The first is to make catalog to be published, and the second is a photographic library of the heavens, sort of charts. Anyway, it is important to have a conference and to speak about this project in April 1887. And that is really also the schedule was suggested by Gill. And also they gave some suggestions also from a diplomatic point of view, how to send the letters of invitation, not directly, but through the academy and through the foreign office. And Moshe entirely accepted the suggestion and really invited all the participants, thanks to the fight for the intermediary of the foreign office. Moreover, he also Gill suggested also the publications of the plates. They can be reproduced on paper and distributed so that any astronomer can have a paper copy of the plates, and can make measurement on this and can do, and it was really made. And also he mentioned that it was an idea that he had also with Captain when he was working to the CPD, but it was too much expensive and they did not made this. They did not make this. But in a certain important international project, they have to also to think about the publication of the charts. The Astrographic Congress was held in Paris in April 1887, and an international permanent commission was established with the directors of the participant observatories, plus members from the most important contributors, a sort of SOC of the Congress. And also they decided to have a meeting every 2 years, but this happened only at the beginning, but then they started to be irregularly. They start to meet in regular frequencies because the project met with many difficulties and problems and started to be fragmented and so on. Anyway, one of the problems since the beginning was that the project was had some ambiguities, especially the ambiguity was between the catalog and the chart. Gill wrote an important report in the journal The Observatory, and he started announcing that the project is focused on making a photographic chart of the sky up to the 14th magnitude. But he also added that another series of plates of shorter exposure will be made and to make the construct the catalog. So since the beginning, from the beginning, we see these two somehow competition between these two parts of the same project. And moreover, of course, we need also some meridian observation to determine the absolute places of the brightest stars on each plate so that the measurement can be made with some reference stars. So the project started becoming increasingly complex. Not only we have the carte du ciel as the star charting, but we have also an astrographic catalog aside, and also we have to prepare a reference stars catalog. So it starts just with the photographic maps of the sky, but it became more and more complex. And what is important is that Gill strongly supported the idea of the catalog more than that of a chart, because he was convinced that the point capital is not the carte photographique du ciel, but it is the catalog that will make an epoch in the history of astronomy. And he also confirmed this idea, writing to Pickering, who was working to his own project of making a star map of the photographic map of the sky. Our true function is the catalog. Even if the chart is much more appealing for the general public, but it is not the scientific core of the project. Scientific core of the project is the catalog. This is Gill is strongly convinced about this, and we shall see that he really drive the project in this direction. Of course, when the initial project became the initial project of a chart became that of a catalog, there was a strong reaction from the international community, and especially in the British context, the editors of the journal, The Observatory, attacked this decision, as they thought that the catalog has been illegally substituted for a chart, and indirectly they attacked Gill because they knew very well that it was Gill that was pushing in this direction, and for this reason. The Moshe was obliged to come in help to Gill and wrote to the observatory a letter assuring that the production, the construction of the catalog will not give any delay to the completion of the chart. As we have already heard, Gill met opposition and was aware that he would have met opposition in his own country. And he didn't have the financial support for the Cape, for the CPD, but he also had to overcome some difficulties for involving the British observatories in the Carte du Ciel project. I think that may be also the usual competition between British and French people was good in this sense, and first difficulties was to overcome the sort of prejudice of the British astronomers and observatories makers in favor of reflector. But for photographic work, it was necessary to have refractors. And for this reason, Gill started a sort of a very strong communication strategy. He went around giving conferences and showing the beautiful plates obtained at the Paris Observatory and trying to convince the public opinion and also the government as a consequence of the need to have refractors for the photographic work. But of course, there is another problem to overcome. The astrograph Henri Gautier was made in France. It was really difficult to accept that British observatories were equipped with French instruments. And for this reason, the British, British instrument makers, Howard Crabb, wrote to Gill, first proposing that he could construct the instrument for the British observatories, but also threatening that if the government send the orders to France, he will take steps to have the question raised in the House of Parliament. So it risked to become also a political affair. And for this reason, all the instrument of the British observatories participating in the Carte du Ciel project were made by Crabb, not only from Greenwich and Cape, but also for the colonial observatories in Australia. Now, if we look at the list of the participant observatories at the Carte du Ciel project, we see that, of course, there is a core from the French observatories, Paris, Bordeaux, Toulouse, and the Colonial Observatory of Algiers. But we can see that there is also another strong group of British observatories and also colonial observatories. So it is the Carte du Ciel has always considered a sort of French project. Maybe it can be considered French-British project in consideration of so many observatories participating in this project. And we also can see here two different approaches from Gill and from Mouchet. Gill has a sort of elitist approach. When some of the observatories, especially those in Latin America, could not carry on their work, he wrote to Gill that there was no reason to be anxious about the problems that were raising in those observatories, because he wrote, I'm not in the least disquieted by the civil war in Chile or other troubles which you describe in Buenos Aires. We shall get from these places precisely what I expected, nothing at all. Why disquiet yourself? It will not be a serious matter if we have to undertake all the southern hemisphere. It's sort of an astronomy of the best observatories, and we can do the work all alone. We don't need other cooperation. And Moshe, on the contrary, was very attentive, a much more inclusive attitude. He really wanted that also as many observatories as possible can give their contribution. So he has a very global approach instead of in contrast with the Gill's approach. And I feel that maybe a similar approach we can find a similar approach later when we compare the different attitude of Kapteyn working on selected areas, also something like the selected the best man, and John Henry Hale, who was working about the International Astronomical Union. I like this letter from Hale to Kapteyn. I think there are great advantages in selecting the best man for the difficult phases of the work, the selected plan of the selected areas, but he preferred that to have a more permanent, so perhaps less effective organization like the International Solar Union. The contribution of Gill was also, as I told you, also about the practical aspect of the project. One of these was that of providing a central bureau of the measurement. He wrote to Moshe, the measurement of the plates can be best and most economically done in a central bureau. And this happened because a central bureau was established in Paris. And Gill also proposed that women's work for this purpose can be procured in Europe at so much less cost than here. And the bureau was entrusted to female staff, and the director was a woman, was Dorothea Klumpke, and it was adopted also by many other observatories like the Toulouse observatories and the Vatican Observatory and others. And even after the death of Admiral Mouchet in 1892 and of his successor, Félix Tisserand, 4 years later in 1896, Gill always remained a consultant for the president of the Commission of the Carte du Ciel, who by default was the director of Paris Observatory. For instance, when the new director of Paris Observatory, Maurice Lévy, trying to relaunching the project, trying to solving the problems, he wanted to replace the southern observatories that could no more participate in the project. He asked the help of Gill for choosing some observatories of the austral hemisphere that can replace the observatories of Rio de Janeiro and Santiago of Chile. Thank you. And for this reason, he proposed that, as we have, John mentioned, the Cordoba Durchmusterung, and of course, Gill proposed that John Thom at Cordoba could replace one of the observatories, maybe La Plata or other ones. And also, when the new director was Benjamin Bayot, the correspondence, even after the retirement of Gill, still was in contact with them. And he, for instance, suggested that the Australian observatories were strongly involved in the project, and also proposed that the observatory of Hyderabad can be also involved in the project and replace one of the withdrawals. And if we look at the correspondence of the Paris Observatory with the Cape observatories, we see that after the retirement of Gill, the correspondence became more intense. And this is because because the new directors wanted to have the support of an important contributor that since from the beginning has guided this project. Other contributions from the Cape, I want to mention also the contribution given by the successor of Gill, Samuel Hall. He made important studies about the overlapping of the photographic plates. I have no time to explain this, but the corner of one plate was corresponded to the center of the other plate. So there was an overlapping. And it was important to study this overlapping in order to identify if there are stars or simply defect in the glass. And he makes this kind of studies, but also investigated the plates constant and also determination of scale correction for different magnitude. And much important, he collaborated to the compilation of reference star catalog with Oscar Backlund. What was the destiny of the project? We know that the First World War, of course, was interrupted. There was an interruption. And in 1919, there was the establishment of the IAU. The first General Assembly was in Rome. And on that occasion, the completion of the project was entrusted to the Commission 23. But more important, the IAU supported also from a financial point of view the publication of the last volumes of the catalog, so that the catalog was achieved, but the chart was left unachieved. And in 1970, it was decided to stop forever the production of the chart. And on that occasion, Paul Couder, who was the president of the commission, wrote that the Carte du Ciel has established the foundation of the international scientific cooperation, introduced the application of photography, etc. Those who have generously cooperated with deserve our gratitude. I think that the astronomers of the Cape are among these that we have to deserve. And if we consider the many reasons that for which the astronomers of the Cape were involved in this project, first, because the Great Comet was induced, the photograph of the Great Comet induced Mouchet to improve the photographic equipment at Paris observatories, because the CPD provided the preliminary know-how for the Carte du Ciel project, because Gill acted as an eminence grise of the project. He suggested the procedures for the invitation, revised the list of invited people, secured the participation of British observatories, convinced the British astronomers to use refractors, oriented the Standing Commission to give priority to the astrographic catalog instead of the chart, suggested the publication of paper copies of all plates, somehow mediated the conflict with Picken, who was working to another competitive project, photographic star map, with in competition. I have no time to enter in this. Suggest also the establishment of a central bureau, proposed the use of male staff, and suggested to involve other observatories to replace the way travels. And also later the study of how, and so that I think that for all these reasons, we can say that without the contribution of the Cape Observatory, no Carducial would have been maybe ever realized. And I think that this crucial role has been is clearly evident from this presentation. Thank you for your attention.
I was about to give the 5-minute warning. Well done. Now nicely in time. Any discussion?
One of the things that you didn't mention was one of the few observatories that actually completed its portion of the Carte du Ciel in a reasonably timely manner was the observatory at the Cape.
Yes, one of the observatories that completed in a reasonable time its work was the Cape Observatory. This is not surprising because, of course, they had now the know-how for doing this. The CPD was an excellent preparation for this work. So they had all the knowledge for doing this work in maybe fast way, much more than other observatories.
Thank you very much for your very interesting presentation. I have a very small correction for the very beginning. You showed a photograph of a cluster in Perseus. It's an open cluster.
So, Ileana, you mentioned the astrographic catalogue was finally completed, was it 1962? What do you think the influence of this was on the science of astronomy? Did anyone actually use it?
Maybe you could stay behind there. I've been asked to have the speaker behind on the stage.
For one of the strange destinies that in astronomy are usual, this catalog was useful many years later because it was completely digitized at the U.S. Naval Observatory. It is very strange because no American observatory participated in the Carte du Ciel project, but the astrographic catalog was completely digitized, and it provided an important reference catalog for all the for the first astrometric missions. For instance, Hipparcos. The Tycho catalog of reference stars that were used for the mission Hipparcos was extracted from AC2000. AC2000 was the digitized version of the astrographic catalog.
Any more? No one?
I must say that now that we have so many astrometric important missions like Gaia, the importance of this heritage is really to be studied. But I have seen that there are contributions about it. Thank you very much.
Thank you. Yeah. And the final contribution from this session is by Zheng Zong Tang. It's Shanghai Observatory. Steph.
Okay.
I have my glasses.
Okay, thank you.
Shanghai Session Observatory contribution to the Cartier project by present future.
Okay, good morning. Thank you for the organizer to give me a chance to introduce our contribution to the CDC project. Okay. My presentation will have 4 parts. First, background. The exchange of modern science, technology, and culture between China and the West started in 1582 when Metronome Ricci came to China. And Ricci brought astronomy, geography, mathematics, technologies, Western literature of his time to China. And also, he introduced Chinese culture, history, geography, products, customs, and medicine to the West. One of the most important work done by Ricci and his Chinese colleague Xu Guangji is they translated the Euclid's Elements of Geometry to Chinese, which is the first important science book to China. In 1872, Jesuit Academy decided to launch Jiangnan Project and successively build a series of scientific, cultural, educational, religious, and charitable institutions. One of them is Skyway Observatory, which is a predecessor of Shanghai Astronomical Observatory. There are many research fields of Skyway Observatory. Astronomy is one of it, but at that time, only meridian instruments worked in Skyway Observatory, mainly for timekeeping. Yeah, you know where about this. In 1887, Paris Observatory initiated the international project to map the sky, CDC. Many observatories took part in this project, and the typical telescope for this project with a diameter of 33 centimeters. In the 1890s, Father Chevalier raised 100,000 francs and ordered a telescope to be installed in Sheshan Observatory. It is an enhanced version of CDC telescope with a diameter of 40 centimeters and a double longer focal length. More than 7,000 photographic plates had been taken by this telescope during the last century. And the targets include asteroids, comets, binary stars, variable stars, clusters, and galaxies. This picture of the moon is the first picture of Chinese telescope, which was taken in 1901. One of the most important work from this telescope is the equatorial catalog. It was observed during 1916 to 1917, and it took 10 years to do the analysis of the plates. And in 1928, the catalog was published in the Sheshan Observatory Journal, and it includes more than 14,000 stars along the equatorial belt. Because of the bigger diameter and the longer focal length, the results of the 40-centimeter telescope are quite good during 1901 to 1940s. And the left picture shows the machine colleagues used to analyze the plates. Okay, following the IAU resolution in 2000 on plate digitization and preservation, we started this work in 2003, and we served many observatories to check the status of plates in Chinese observatories. And in 2009, the plate digitization laboratory was created in Sheshan. And about 30,000 plates of all Chinese observatories were transferred to the plate archive of Sheshan Observatory before 2008. Under the support of Ministry of Science and Technology of China, the laboratory carried out the project of digitizing Chinese astronomical plates during 2012 to 2017. This table shows the basic information of all Chinese plates from different observatories and different telescopes and the time period. And this photo shows the number of plates in different years. Before we started the digitization of Chinese plates, we used two commercial scanners from Epson company to test scanning the plates. But the results showed that both scanners had big errors in positioning and photometry. You can see the right picture. The distortion of the digitizer is about 20 micrometers. And also the uniformity of the photometry is not very good. So we decided to develop one special digitizer, similar like Harvard and Brussels, to digitize our plates. And we did this work jointly with Nishimura company from Japan during 2013 to 2016. And in the next 2 years, we finished digitization of all 30,000 Chinese plates. Later in these 2 years, we have done some systematic analysis of the plates. One is photometric calibration. We use the magnetic term, color term, and flat field term to get a reliable magnitude. This show one sample of plate result from Yunnan Observatory. And finally, we get the photometry of 0.08 magnitude after the calibration. So these are very good results from the old plates. And in this year, we published the astrometric and photometric results from half of Chinese plates in the National Astronomical Data Center. And also we published a paper about this analysis. After we digitized all Chinese plates, our work were recognized by Shanghai local government, and they suggested us to provide service to other research fields like remote sensing, surveying and mapping, medicine, biology, and so on. So under the support of Shanghai government, we developed 4 new digitizers based on air bearing techniques. And now we have the capability of digitizing 100,000 plates per year. You can see the photos of 4 digitizers. All these digitizers can be used to digitize astronomical plates. And one digitizer can be used for colorful digitizing and for reflecting digitizing. And one digitizer can be used for scanning large plates. And another one, the right one, is for the film digitizing. The operation mode of our digitizer, each plate is scanned in many sub-images, and then we combine them to one big image, like a zigzag pattern in this picture. The size of each sub-image covers 1400 times 1400 pixels, and each pixel is about 11 micrometers in square. For one 30 centimeter times 30 centimeter plate, the scan costs about 3 minutes. So it's a very fast machine. Compared to the PDS, it needs 24 hours for the digitization. For the calibration of the digitizer, we used one special dot calibration plate. And we use it for calibration of distortion and misalignment, and also the positioning. Because this plate has more than 90,000 dots and distribute evenly. And each dot has really good positions, and the precision is better than 0.2 micrometers. So which is like a standard plate. This picture shows how we use this calibration plate to determine the distortion of the digitizer. So because this distortion is stable, so we can use this to collect the digitized images. Okay. And also we use the calibration plate to measure the misalignment of the two coordinate system. One is the CMOS camera, another is a platform. And after the adjustment, the residual errors in positioning is smaller than 0.1 micrometers. Okay, the same for the shifts. We can get also very high precision after the adjustment. After the debugging of the digitizer, we also need to do a performance test. And the first is the preheating time. Based on my experience of using PDS, it needs 24 hours to warm up the machine. For our digitizer, it needs about 1.5 hours to warm up. So every morning we need to turn on the machine and then waiting for 1.5 hours. Okay, thank you. And also when we adjust the brightness of LED, we also need about 10 minutes to wait it becomes stable. These two pictures shows the intensity changes along the time when we adjust the LED brightness from 200 to 600 and from 600 to 200. So when we digitizing plates with different transparency, we fixed the brightness of the LED and adjust the exposure time based on the transparency of the plate. Another issue is flat. We take 1,000 images to generate the flat image and then collect other images with the flat image and calculate the deviation. The bottom figure shows after the collection of the flat, the non-uniformity of the plate is very small, than 1%, and within 16 hours, which means the flat is really stable. Another important issue is linear response, because we use the LED and the optical lens and also CMOS camera. So we need to know where and how the linear response. We use a different exposure time to scan the plate and then compare the exposure time and the corresponding intensity of pixels and calculate the fitting residual. The left image shows generally the linear response is quite good, but after the after the residual was calculated, we found that when the intensity is smaller than 30,000, there is obvious non-linear response. So we need to collect this. Yeah, we are happy that this non-linear response is stable. You can see the middle image. We scan 10 times and the non-linear response is the same. So we can collect it from the test scanning. And the right picture shows after collection of the non-linear response. And all these can be reduced to 0.3%. Okay, so it's very important for the good photometry from the plates. And also about the dynamic range, we use different exposure time and to check the intensity of pixels, whether they are changed along the exposure time. The left picture shows very short exposure time from 0.05 millisecond to 0.2 millisecond. And the right picture shows from 998 millisecond to 1002 millisecond. The intensity changes with exposure time, so which proved that our dynamic range is about 4, so it's enough for the plates. And also we test the photometric repeatability. We scan one plate for 5 times and then compare the instrumental magnitude of all stars. You can see that the eye mass of the repeatability is smaller than 0.01 magnitude. So it's good enough for the plates. And also we compare the plate digitization for different orientations, 0 degree, 90 degree, and 180 degrees. And then we compare the instrumental magnitude of the same stars and get the residual. From the picture, you can see that the eye mass of difference is smaller than 0.03 magnitude, and there's no systematic differences. Okay. The positioning repeatability is very good, about 35 nanometers, because we use the air bearing technology. And also we rotate the plates to get the difference of positions, and the result is very good to 0.17 micrometers. Okay, in the past 3 years, we digitized the plates from Italy, Uzbekistan, and Chile, and all plates have been sent back to their home country and safely. And here is some initial results from the plates of Uzbekistan of 2 asteroids. And these pictures shows digitization work of Shanghai Natural Museum, colorful digitization. For the future plan, in the past 5 years, we have signed agreements and MOU with other observatories, and this Torino and Chile, and Argentina and South Africa observatory. And we will cooperate with South Africa and Argentina observatory to digitize their plates. And under the coordination of the PDPP working group, we are willing to cooperate with observatories all over the world to digitize the historical plates, especially the CDC plates, to do research long-term domain astronomy, and based on the digitized data. Thank you for your attention.
Any discussion?
Thank you. I have just a question for you because, as far as I know, there is no official connection with the CART-UCL project. Who was the astronomer that ordered the instrument? And have you any correspondence in the archives with Paris observatories and with other observatories participating in the project?
Okay, for CDC, the telescope was not the official participants, but the father, that time, they ordered a similar telescope and a similar observational mode and a similar analysis method to do this research. You mean at that time or now? The father, okay, sorry, I need to go back. Okay, Chevrolet. He was the director, and he used this telescope for more than 20 years, and he published many works. Yeah. Okay.
Any more?
The background knowledge in this, Chris Corbally.
Yes,
Yeah.
yes.
Could you describe now your project of sending a set of, as it were, test plates around the various digitizing centers like Paris and Harvard? That'd be helpful.
Yeah, in last month, we took our plates, some astronomical plates, and also the test plate to Paris. Yeah, Unfortunately, their plate holder is exactly 30 centimeters times 30 centimeters, but our calibration plate is 32. 32 okay, parameters, centimeters. So we will order another calibration plate to fit the size. But we have digitized our astronomical plates, and now we are analyzing the positioning and the photometry. Yeah, yeah. Okay, we will check with colleagues in Harvard. Yeah, yeah, sure. Yeah, that's a very important. Yeah, job.
Any more discussion?
As far as I know, the Sikaway Observatory was in connection with the Italian Spectroscopic Society for the solar monitoring. Have you any photograph of sunspots?
Yes, yes. Yeah, in our Susan planet cup, there are many plates of the sun.
And what about the correspondence, the archives of the observatory? Is it possible to have access to letters
Yeah, yeah,
from
sure.
that time?
Yeah, yeah, no problem.
Okay, we keep in touch.
You're always welcome. Yeah, no problem.
Thank you. Any more discussion? If not, then thank again all the speakers of this session.
Okay, thank you.
We reconvene at 1:30. See you then.
See, our world is slowly dying. I'm not wasting no more time. Don't think I could believe you. My hands are getting my hair is church is not starting. The house is quite strong. Mr. Father, there's no feeling. Don't you Rise be silence and when I must be better. Don't think you will forget me. You never said a word, you didn't send me no letter. Don't think I could forgive you. See, our world is slowly dying. I'm not wasting no more time. Don't think I could believe you. Yeah, our hands are flowing, thoughts in my hair, please. Think I could forget you. As you see, church is not starting. The house is but strong. Think I could forget you. It was great at the very start. So each other couldn't stand to be far apart. Closer the better. And we're picking sides and stand. Talk right. To belong to just to sing like we're over is the to belong the first time lose track of us. Lost the paper. Defines pine out of touch. If you come fear, messed up facts. Sorry, don't talk about what's the Standing at the back of mine. It's to leave you actually yeah. Yeah, don't scream. There are so many roads now. Some
You feel unless you fade away, fade out in this atmosphere. See it.
Saying like rules every time. You twist the mood. Go down to brand new. I'm trying to stay up to try to play cool. Maybe I play my rules every time. Every mood.
Okay, welcome back. This meeting six of history of astronomy in South Africa. And it said, we've been talking of photographic monitoring in South Africa. The three speakers, Jan Glass, Sharon Shipment, and Christian Spector, are well known for this in the field of history of astronomy. And I have the pleasure to invite the first one, Ian Glass, who will give a talk about the South African observatories and technological change.
Thank you very much. The same rules, 10 minutes and 5 minutes.
Yeah, thank you. So this is a very general type of talk, touching on quite a few of the things that we've heard a little bit about already. You basically know the effect that people like Tycho's fantastic improved ordinary telescope-less circles had in astronomy. Also, of course, what Galileo did. Those things, in a sense, those innovations made a big difference in the whole history of astronomy. So I'm emphasizing the technical changes that happened with us. Just to give you some orientation, the Dutch East India Company, the VOC, arrived in 1652, 1656. And now the first important astronomy was done by Lacaille. He was a French astronomer, member of the Royal Academy of Sciences in those days. And Cape became a British possession, 1806. And the Royal Observatory, which still exists in some form, started in 1820. And one of its first achievements was the first parallax observations of Alpha Centauri, which was really the first observations that led to the distance to a star. But of course, he didn't publish on time, so he got scooped by Bessel. But nevertheless, he had made the observations. And so the Herschel surveys around 1834 to 1838, we've heard a little bit about as well. And of course, the CPD happened in 1885 to 90 or so. So one of the first visitors was a Jesuit team on their way to Siam or Thailand. And they are really the first serious observations that happened at the Cape. They had a telescope, that really the latest equipment. And of course, Cassini's tables of Jupiter's moons were very important. They dated from 1668. So that way you could get absolute timing from wherever you were on Earth if you could see Jupiter. And of course, the pendulum clocks had been developed not very long before that. And they had a very good one by Turel. And of course, he had worked with Huygens in Holland. And from the frontispiece of their book in the bottom left corner, you see the kind of instruments that they had in those days. And of course, those of you who know the Paris Observatory, the instruments depicted on the front wall of that are very similar. This is just to give you an idea of what was happening in terms of progress in astrometry, which of course was very fundamental in those days. Usually the red dots are basically the southern ones. And you see the first one from de Houtman before they started observing from South Africa wasn't terribly accurate, but generally speaking, later than that, the observations made down here were very comparable to what was going on in Europe at the same time. Well, Lacaille came 1751. He built a little observatory on Cape Town foreshore. This is my reconstruction of it. Had a number of very simple instruments, worked on the meridian mostly. And he made a systematic sky survey from more or less from the tropics, from the Tropic of Capricorn to 90 degrees south. And he used a 3-foot quadrant, which was on the meridian the whole time. And he could look at 3 degrees of sky at a time. And he let the sky drift over. And he stood there with his eye glued to the telescope for hours at a time. Some positions he had a little headrest so that it helped him to keep his head in position. But he had to note when stars passed through his reticle and what the time was. And you see at the bottom his reticle, which is 3 degrees across. So as a star entered the reticle and left the reticle, he could take the average of those times, and that would give him the right ascension, and he could work out the declination by the difference of the times, because if you were near the end of the trapezium, of course it was short, and if it was in the middle, it was long, and he had to note whether it was the north or the south part of the trapezium. So he found position for nearly 10,000 stars to about 30 seconds of arc accuracy. So this was actually a complete sky survey. I mean, it wasn't just spotting stars and getting their positions. I think it's probably the first time anybody had done this. And he said you couldn't do this in Paris, and because, of course, the weather wasn't good enough. You didn't have many hours. In fact, Herschel said he got about sort of 10 good nights a year capable of doing that kind of work. So, then the next step I want to mention is the observatory in Cape Town. It was installed, the equipment was installed about 1828. And it was similar to the best equipment they had at Royal Greenwich Observatory at the time. And basically it had a transit circle, a mural circle, and a clock. And they were able to get probable error of one observation quite down, well below 1 arc second. And of course, this was very important in the next step. So the first parallax observation was made by Henderson, who was the second of the Her Majesty's astronomers. Well, as you know, Copernicus, 1543, his publication said, you know, you should be able to detect parallax. And of course, many people tried to detect parallax. And the usually instrumentation just wasn't precise enough to do this. But what happened is there was a small observatory in St. Helena founded by the British East Indies Company, and the observer there had found that Alpha Cen had a very high proper motion. So it was a very bright star, very easy to observe. So Henderson actually heard this, and he made enough observations in about a year to get a parallax. Of course, he knew already what the proper motion was. So he claimed, and unfortunately for him, he sat on his data, and he was very worried about some properties of the instrument. So he didn't actually publish until after Bessel had published. Only about a month later, I think, he sort of thought, well, okay, I better go with my data. But I've never seen any evidence that he appreciated before that time that he had discovered the parallax. Anyway, he claimed a parallax of just over a second of arc, and nowadays it's reckoned to be about 0.74 of a second of arc. Now, Bessel's result was much more precise using a heliometer, which was a kind of differential instrument for measuring the position difference between two stars. But nevertheless, people agreed that Henderson deserved at least some of the credit for the first observation of this kind. So just after that, John Herschel came along, and he set up the famous telescope you see on the left. It's essentially his father's telescope, more or less rebuilt to replace all the rotten wood that had accumulated in the meantime. And we have one of his mirrors actually in our museum in Cape Town. And on the right, you see a picture of the estate called Feldhausen, where he had his telescope. And he had a small equatorial telescope as well in that other hut. So the position where that telescope is now marked by an obelisk. It's a heavily built up area now, and it's in the kind of courtyard of an elementary school. But you can actually see it from the road, and I've been there a couple of times. But it took, of course, a whole team of people to operate all these winches and things when you were observing. And of course, he used this offset Newtonian type, offset prime focus type of telescope. And the images are pretty terrible. And you can see hanging on the railings of his observing platform a number of interesting appetizing masks. So in some circumstances, he would actually put a mask in front of the telescope to improve the image in certain particular ways. Anyway, the next very important thing that happened, which we've heard about a fair amount about already, was the improvement in photography that happened around then. Emulsions had become much more sensitive in the late 1870s, and they were slowly percolating into the astronomical world. And in fact, what got Gill going is on the bottom right, you see this little photograph, which was taken by an amateur, probably with an undriven lens. And so Gill saw this and, of course, decided they'd have to try and do better. So he got this chap called Alice to lend him that lens that you see there. It's in our museum as well. And the photograph on the left is one of Alice's first photographs. But of course, as was pointed out before, the stars were visible in the background. And of course, this inspired people to realize that this was the ideal way to map stars, to make a catalog where you could look at a lot of stars at once, and much less labor than having to go one after the other like they did in the Bonn Dirkmusterung. So it wasn't easy going. Gill eventually got the lens you see in the top right here, and we still have that lens, but he had hoped to do better than that lens could do. That gave a certain limited field, but he asked Grubb to design a better lens. And the one on the top left, the big one, is actually the lens that Grubb built for him. It wasn't very successful, in fact, because I think Grubb didn't appreciate the requirements of having a wide field. Up till then, they were quite used to having a good field on axis. And to actually get a good field was another thing. And of course, they got advice from the best opticians of the time. But even so, they found that this lens, which was financed by Naismith, just wasn't good enough. And of course, they had to have a guider and everything else. So the bottom left telescope was an experimental telescope to test out these lenses, and it wasn't really successful. So they actually went back to this Dallmayr lens at the top right. And the survey was made from that 6-inch lens with 54 inches focal length. So as was mentioned, Grubb managed to get into a collaboration with Kapteyn at Groningen, and they designed this special parallactic instrument, the idea being that the plate was mounted more or less at the same focal length as the telescope itself. So you're essentially almost observing the stars with a right ascension and a declination scales. And so the famous CPD catalogue by Gill and Kapteyn was published over a few years, and it contained positions for 454,875 stars. So, and then of course up at top right you see Kapteyn, a famous picture of him. And actually Kapteyn's picture, the top right of it, there's a picture of Gill, which was always on his study wall apparently. So this was followed by the Astrophotographic Congress in Paris in 1887, which of course resulted in the Carte du Ciel project, which is a kind of precursor of the IAU because it's the first big international collaboration in astronomy. And Edmund Rouchet and David Gill and others pushed for this project, and they settled on this idea of standardized 13-inch or 33-centimeter photographic refractors and 10-inch visual guide refractors. Because of course, to be able to take long exposure photographs, you had to guide them. And the telescope drives were not all that great in those days. So it was really quite important to have a guide telescope and means of illuminating a reticle and the best possible drive. So the Cape astrographic zone is given there -40 to -52, but Grubb was finally given the contract to build British telescopes. And in fact, you heard about how he had to lobby Parliament, and he was prepared to go to a lot of trouble, very much like a defense contractor these days, to make sure he got the contract to make these telescopes. But they found that they thought the Henry brothers' telescopes were their lenses were better quality. So Gill put pressure on Grubb to do better. So Grubb spent a lot of time fiddling around, trying different combinations of lenses, different with the flint in front or the crown in front, and different curvatures. So you'll probably find that quite a lot of the telescopes he actually made were not identical. Anyway, there was constant correspondence, which we still have, between Gill and Grubb, asking him to fix that or do this better or that better. And Grubb got more and more fed up because, he thought he'd got a contract for a fixed amount of money, but the client kept asking for more improvements. Anyway, he had to go to new levels of drive precision, but he couldn't get a doublet field better than about 2 degrees by 2 degrees. But they got G.G. Stokes, who was a famous physicist at the time, to act as a consultant on the lenses. But really, I don't think Stokes knew as much as, say, something like Abbe in Germany did at the time. But these are some of the things about the interaction. In the top left, Gill designed methods of holding the photographic plate so they could be tilted nicely and very carefully squared on, and the focus tube moved evenly and so on. And down the bottom left is a diagram of a kind of chronometric drive system that was linked to the observatory time system. And on the right bottom is how they cut the gears they were able to cut much better gears than was possible before. And you see somebody working with obviously precision instruments, Victorian style. So to measure the carte du ciel plates required special instruments, and Gill actually, the Repsold had designed a few instruments, but Gill designed this particular type of instrument, which he felt was going to be the best method of doing it. And there were 2 of these made, which we still have, as well as several other instruments of later date. So this was one of the important things they had to do. So after this point, Innes came to work at the observatory. He had a quite interesting history, but he was an amateur astronomer, a liquor dealer, who actually became one of the main double star observers. But one of the things he did while working for Gill was to look at second epoch plates to find stars that had high proper motions. And after his work at the observatory, he was the director of the Johannesburg Observatory, and they got hold of the Franklin Adams telescope from a British amateur. And on this, looking at plates taken about 3 years apart, very poor quality plates, I must say, but using the blink comparator, he was able to find the star we call Proxima Cen. Now, he believed it had the same proper motion, he thought, as Alpha Cen, and he claimed to have managed to measure the parallax, but really, given the accuracy of his equipment, he couldn't do that properly. But nevertheless, he called it Proxima Cen, and he made a lot of noise that it was almost certainly the closest star. It was also about the lowest luminosity star ever discovered at that time. But this guy Wout, who was a Dutch volunteer working at the Cape, he actually did some photographic parallax work on Proxima using astrographic plates. Now you can imagine the astrographic plates didn't have such a great plate scale, but it's better than nothing. But he could prove at least that you couldn't say for sure that Proxima was the nearest star. And actually it took really the space telescope and some of the astrometric telescopes, astrometric satellites lately, to actually prove that it is the nearest star known. And so far it's still the nearest star known. So, yeah. Oh. And anyway, the Yale telescope was put there by Schlesinger and company to do a series of parallaxes in the southern hemisphere. So it was one of the first foreign telescopes to be installed in South Africa. I mean, well, they're all foreign, but the first new expedition in the 20th century. So one of the curious things is a successor of Innes at the what became the Union Observatory as it became was this guy Finson, and he designed an eyepiece interferometer, and with that he could actually observe closer double star than was possible by traditional eyepieces. The other thing he did that was quite interesting was he did high-speed Mars photography and image selection. So it's the first example of that type of work, which is, of course, very popular nowadays. It's all done by CCDs and computers now. So there's a whole bunch of southern telescopes, and some of them still existing. Yale, that's closed. Boyden, Leiden, of course, had the collaboration with the Union Observatory, and there was a small one, Brukeras, which I think was Smithsonian. And then the Redcliffe 74-inch was the first big telescope in South Africa, and the Lamont Hussey Observatory in Bloemfontein specialized in binaries as well, but Eyes actually worked there and did a famous H-alpha survey. So this is the 74-inch telescope, which was the 5th largest in the world at the time. But the first important discovery it made was of RLR stars in the Magellan Clouds. And that showed that, in fact, Hubble's estimate of the Hubble constant was not right, and by about a factor of 2. Well, I mean, since then, it increased by an even larger factor. But it was the beginning of the sort of modern understanding of the size of the universe. And so it was also used high-resolution spectroscopy of emission line stars like Eta Carina, those classical studies of, and the most luminous stars in the Magellan Clouds. These were all very important stars, very important projects, you know, pointing out the limit of stellar mass, really, and what happened, which stars were the most massive and most luminous. And that telescope was moved from Pretoria to Sutherland in 1974 to 1976 when the Radcliffe Observatory closed down. And its beautiful orange color was based on the color of our refrigerator. So the Leiden Southern Station, that was built originally in Johannesburg, but then in 1954, they founded a field station, and most of the usable telescopes were moved out there. And of course, that was part of the trend to move to places with dark skies and so on. And one interesting thing there was the Valraven automatic photometric telescope that had simultaneous multicolor photometry, but also pre-selecting of the stars. So it was a very efficient telescope to use for star-by-star photometry. The Boyden Observatory was originally, well, we'll hear more about it, but it was originally founded by Harvard in Peru. And when it came to South Africa, they put up a 60-inch Newtonian. It wasn't very successful, unfortunately, but it was somewhat usable. But the most important discovery there was the Fornax sculptured dwarf ellipticals. It was the first example of dwarf galaxies that was found with the Bruce 24-inch telescope by Shapley. And then they built the Amar Dunsink Harvard Baker Schmidt, which is the first Schmidt telescope in the Southern Hemisphere, big one anyway. And the most important thing, I think, from that was probably the Hodge Wright Atlas of the LMC. There may have been other things, but I'm not too familiar with that. So we carry on to pioneering photometry. We heard about the problems of Southern Hemisphere photometry, of ordinary photographic photometry, and people like Howell and so on, and then other people from the observatory were concerned with improving photographic photometry. But this chap, Cousins, was an amateur astronomer who was interested at first in Fabry technique, which is a kind of out of focus density measuring technique rather than diameter measuring. But then he very rapidly got on to photoelectric photometry, partly as a result of some American expeditions to the Cape. And so his first photometer is the one on the left. You see it on the astrographic telescope, but his standard photometers were like the one on the right, which he used more or less his whole career. But he also was the originator of UBVRI, and his precision was appreciated worldwide. He was mad keen on precision. I mean, that was his main interest in life, although he did some interesting discoveries as well, I haven't time for. So anyway, this is the new world of 1972 after satellites and the general expansion, radio astronomy, X-rays, infrared, and so on. So we got heavily involved in infrared, and as well as, of course, people had experiments on satellites, were getting data from satellites. So this being my baby, I couldn't help telling you about it, but this top left picture was actually done by scanning with a single detector, 477 scans, 10 minutes each. So I can tell you that was quite a marathon. And then on the top right is the one of the Jupiter collision, Schumacher-Levy comet collisions with Jupiter. And the bottom left is a infrared survey facility that's from the Japanese in South Africa. And then, of course, we found a period luminosity relationship for MIRAS, which was quite an important step forward. Of course, you don't see that invisible, you see it in the infrared because of the fact that the spectrum is so eaten into by absorption bands. And so we developed this platinum silicide infrared camera as one of several, and that was used for that Schumacher-Levy one. Okay, our present large telescope, it's a 10 by 11 meter mirror, and it's about 50% owned by South Africa at the moment, I think, and had a relatively economical construction. And I think you can see how it was constructed, but it's quite different from a fully steerable telescope. So it's very efficient in some parts of the sky and not so efficient in others. The Meerkat radio telescope, of course, is a big South African thing, and it's been very successful. It's a precursor of the SKA project, and it's been used, well, I suppose it's been about 4 years. And at the last IAU, they announced this big meerkat image at 23 centimeters, showing all these very interesting features in synchrotron radiation and other things. And of course, this is just the beginning of the whole SKA project. There's an awful lot more coming there. The last thing I want to show you is the Hess Gamma Ray Telescope in Gerlschau in Namibia. This is a fantastic thing. It's from the Max Planck Institute for Nuclear Physics in Heidelberg. They're the sort of prime people, but it's an international project with many participants. And you see there, they can actually photograph the air showers caused by high energy gamma rays interacting with the Earth's atmosphere, and they can trace back the direction that they came from. So it's been the gamma ray telescope, high energy gamma ray telescope, that everybody admires the results of. So it's opened up a whole new part of the electromagnetic spectrum that really wasn't accessible properly before. So that's the end of my talk. I hope there's a minute or two for questions.
Thank you, Ivan. Yes, we have 2 minutes, so there is time for questions. Please.
David. Of which was?
Do you know how wide a field the Henry brothers were able to get with their lenses?
Sorry, of which?
The Henry brothers, the Henry brothers.
Oh, the Henry fields. Yes, I'm sorry, but you saw some pictures earlier that somebody else showed, which would give an idea. But I think they would have been limited to something similar, because I think it's a kind of fundamental limitation of a two-component lens. So I would guess 2 by 2 is pretty good for if you want, images that are smaller than half an arc second or an arc second. Yeah.
Ian, you have been one of the promoters or founders of infrared astronomy in the Southern Hemisphere. And I wonder whether you could tell us some personal stories, how you got into infrared astronomy
how you got into young stars.
Uh,
I remember I studied one of your stars called Glass Eye,
Yeah, I remember
which
that.
is a Tauri star, a binary Tauri star, and one star is in the optical and the other is not seen because it's in the infrared. The so-called infrared companion, which you were one of the first also to find this.
Okay, well, the whole story of getting into infrared, it started, I was interested in Michelson's stellar interferometry, and Neugebauer happened to hear about this, and he offered me a postdoc. So I went to work for him for about a year, and I learned all about infrared, and it was a field that I really took to. And of course, it turned out Royal Greenwich Observatory wanted to get in for infrared, and so they hired me after that. And well, they sent me out here, and so it's from that point onwards. So that's how I got into it. So Glass Eye, I was always amused. I made a list of stars that I'd looked at in a dark cloud, and I labeled them A, B, C, D. Now it so happened he picked up on I and wrote a paper about Glass Eye. Yes.
Thank you, Jan. I think thank you very much for your
Yeah.
presentation. I think that it's time to invite Sarah Schachner, and she will present her talk about Harvard's Boyden Station in Bloemfontein. Please.
Okay, hello everyone. It's nice to be here. So I'm going to talk about Harvard's Boyden Station in Bloemfontein, but since the instruments that went there had a prior history and the context is important to understand the Boyden project from its prior incarnations before being reconstituted here in South Africa, we're going to start back in Cambridge, Massachusetts. So, as happens with many observatories, a site once chosen can fall out of favor. And this was certainly the case of the Harvard College Observatory. When it was built, it was situated kind of on a hill in a rural part of Cambridge, but soon it became encircled by houses and the bustle of the city. And additional telescopes started to sprout like mushrooms around its yard. And these were dedicated principally to photometry and stellar photography, a field in which the Harvard College Observatory was a pioneer. Indeed, the first ever photograph of a star was taken there in 1850. And some 30 years later, director of the observatory, Edward Pickering, who you see here, and his brother William picked up that baton of photography and ran with it. In 1885, E.C. Pickering had Alvin Clark and Sons of Cambridge correct a Voigtlander lens of 8-inch aperture and 45-inch focal length for celestial photography and have it mounted in what became known as the Beisch telescope. And you see a picture of it here. And this telescope will come again, and we'll see it many times in this story about Boyden. And soon after this, larger photographic telescopes followed, most notably a 13-inch refractor built in 1889 and a 24-inch photographic telescope known as the Bruce, which saw first light in 1893. And both these telescopes were by Alvin Clark and Sons. The 13-inch refractor is more commonly called in the literature the Boyden telescope, even though it's sometimes called the Clark 13-inch because of the Clark connection. And here you see it in its modern state, as well as some historical pictures. It had a very unusual optical construction designed by Pickering in consultation with the Clarks. The crown lens was reversible, and in one position was suitable for visual observing and in the other for photography. Now, the 24-inch Bruce telescope, which you see here being tested in Cambridge, was a doublet. That means it had two crown flint pairs, and it was funded by a $50,000 grant from Miss Catherine Bruce an unmarried and very wealthy New Yorker. And it took very large plates of 14 by 17 inches. The lenses and cells were recently recovered and restored by Ken Lowney, who is in the room here, and are now on display at Harvard in the collection of historical scientific instruments. Now, each of the Bruce plates could contain as many as 100,000 celestial objects, and when it was completed, it was the most powerful telescope in the world. An objective prism was made for it that could go on the end of the tube and thereby enabling high-quality photographs of stellar spectra. By the time of Pickering's death in 1919, Harvard had amassed a library of more than 100,000 glass plates. Today, there are over 500,000. These plates were used for the discovery and study of variable stars, novae, clusters, and nebulae, and the classification of stars by their stellar spectra. Well, Pickering's program of visual and photographic photometry and spectroscopy, known in the literature as Harvard Photometry and the Henry Draper Catalog of Stellar Spectra, had as its goal the cataloging of the entire sky. And since only 3/4 of the sky was visible from Cambridge, which was a latitude of 42 degrees, Pickering recognized the need for establishing an observing station south of the equator in order to extend these Harvard surveys. And he also desired a high altitude observatory where the atmosphere would interfere less with seeing. Now, an opportunity to achieve both came in 1887 with a bequest from Uriah Boyden's estate, which was about $238,000. And after testing sites on Pikes Peak in Colorado and Mount Wilson in California, Pickering sent an expedition to Peru and Chile under the leadership of Solon Bailey. Now, a number of locations were tried out, and the best seeing was Chile's Atacama Desert, which is still highly desirable for modern astronomers, as you know. But at the time, that site was too desolate. Workers, food, and water would need to be shipped from the coast. Arequipa, Peru, which you see here with the semi-extinct volcano El Misti in the background, was a town of 30,000 and had a railroad, and it was surrounded by the high desert elevated over 8,000 feet. And here is the observatory. That in 1890, this site was chosen to be Harvard's Boyden Station. Now, getting the equipment, I mean, we've been talking about all these equipments coming to the Cape and elsewhere in the prior talks, and transporting equipment to any of these places was not easy. The shortest route from Cambridge to Arequipa was overland across the Isthmus of Panama. So this meant shipping to Colón, going by train across to Panama City, and then by ship to Mollendo, Peru, the closest port to Arequipa. Now, Pickering thought that all that shipping, loading, unloading, transport by train, and all this across Panama was too risky for the precious Bruce telescope. So he was determined that it should go all the way around the Cape of South America and up to Mollendo. The crates were taken to New York first by Professor Willard Gerrish, an astronomer and the observatory's chief engineer. And there he oversaw the loading onto a steamship, the SS Condor, which looked much like this one of the same period, and insisted, though, that the tide had to bring the ship's deck up to the level of the wharf before they would load anything onto it. And then the lenses were placed in the ship's treasure room. The ship then sailed, around the tip of South America, through the Straits of Magellan and up to Mollendo. Now, that was the easy part. A drawback at Mollendo was that it lacked a harbor. Ships had to anchor offshore, and passengers and cargo were ferried to and from shore through what was a seasonally very rough surf in a lighter. A lighter is a shallow boat or barge. Now, this procedure was precarious because not only you see a postcard of this typical summer surf there, but that when they got from the boat or to the wharf, people and goods had to be hoisted in this net up or down to the wharf. And here you see a herd of cattle being loaded onto a boat. You see the shallow boat. If you look close down at the bottom, you'll see little horns sticking up and cattle, participating in this loading. And so imagine doing this with your precious observatory instruments and glass plates. So once stuff got to this point at Mayendo, Bailey supervised all this unloading and the stuff being rowed to shore and then loaded up. And then it went by railroad to Arequipa. And the final leg of the journey to Boyden Station was by wagons pulled by oxen. Now, the first instruments he took were 4-inch meridian photometer, which had been used to extend the scope of Harvard photometry to the Southern Hemisphere, and that 8-inch base telescope that we saw earlier, which had been used for stellar photography and spectrum plates to advance the Henry Draper Memorial. Now, both these instruments had already been employed in Cambridge for the same purposes, and this meant that the observations would be strictly comparable, those made in the South to those in the North. And as we'll see, this duplication or twinning of observatory instruments guided Harvard's development of its stations in both hemispheres. So the photometer returned to Cambridge with Solomon Bailey in 1891, after which E.C. Pickering's brother, William, arrived to take over the Southern observing station. And William brought with him the 13-inch Boyden photographic telescope and a little 2.5-inch Voigtlander photographic doublet, which was called the Bashito or the Little Bache. And he also oversaw the setting up of these various other observatory structures, the building of a residence, a laboratory, and various other outbuildings. He was there for 2 years, getting himself into financial trouble and being called back by his brother Edward and the Harvard Corporation. And Solomon Bailey returned down to Arequipa. And then there was a succession of directors that came and went until 1927, when it closed over a period of 36 years. Now, in addition to running the observatory and shipping crates of glass plates back to Cambridge for analysis, that means the plates went back, hauled up and down onto boats through the surf and all that. Bailey and staff members in 1893 set up a meteorological station at the summit of El Misti, which was about 11 miles northeast of Arequipa. This is the nearly extinct volcano. The altitude there was 19,200 feet, which made it at the time the most elevated scientific station ever maintained. In 1896, the 24-inch Bruce telescope arrived in Arequipa, and we've seen some pictures of it already. And the last major instrument to come from Cambridge was this instrument, the 10-inch Metcalf triplet. Here we see it in its present incarnation in Bloemfontein. And it arrived in 1918. It had been built by the Reverend Joel Hastings Metcalf for Harvard in 1915. Now, life in Arequipa had its trials. Civil War in Peru from 1893 to 1895 caused the telescope lenses on several occasions to be removed and buried for their protection. Robbers broke into the shelters on El Misti and stole the meteorological instruments. In 1896, there was a major earthquake. Harvard College had to cut back its spending in 1909 when Mrs. Draper the funder of the Henry Draper Memorial, cut her support for research by more than 50%. And of course, World War I caused problems in transport, communication, and staffing, which led to the shuttering of the station in 1918 for a short period of time. Now, as productive as Arequipa was, it had a cloudy season that could last for 4 months. So Pickering had heard from astronomers Sir David Gill and Sir William Morris about better prospects to be had in the high plateau of South Africa. Therefore, as early as 1908, Pickering sent Bailey to explore alternative sites. Bailey came equipped with various equipment to test the seeing and a camera, meteorological apparatus, telescopes, and preliminary visits were made to the Cape Colony, the Orange River Colony, the Transvaal, and what is today Zimbabwe, then called Rhodesia. Selected for more detailed trials were Hanover on the Upper Karoo, Bloemfontein in the Orange Free State, and Worcester. And Bailey's logbooks for observing the seeing at these stations survive in the Harvard archives. Here's a selection of pages dealing with Bloemfontein. On the plus side, Bailey found that the amount of clear sky during a year was better than Arequipa. The steadiness of the atmosphere was not better, and the diurnal range of temperatures and dew were worse. Plus, there were severe thunderstorms, dust storms, which were concerns. But Bloemfontein had not only the most favorable weather, but was a location that could offer some society for scientific staff. So, however, the financial straits of the Harvard College Observatory did not permit a move back in 1908 when this survey was done. So when Pickering's successor, Harlow Shapley, became director in 1921, the wish to relocate Boyden Station was still strong and was reinforced, Shapley confessed, by ongoing political problems in Peru. In Peru, he said, we met with a difficult type of government where we had to work on a sort of bribery system. On the other hand, he said, we thought we could get money out of South Africa better than we could out of Peru, and we needed money for new telescopes. So here you see Shapley sitting at this rotating desk, which had been built for Pickering, and then Shapley liked to use it as well. And it was used to manage all the observing stations. And one part of the desk today, you can still see remnants of a label marked Boyden Station. So in 1926, Shapley found the money. It came from the International Education Board of the Rockefeller Foundation and Harvard University. A selling point to the Rockefeller Foundation was the argument for a very big telescope on a new site and an ambitious program. So in November 1926, the Arequipa instruments were dismantled and in February 1927 shipped to Bloemfontein by way of New York. An exception was the Bruce 24-inch telescope, which was diverted to J.W. Fecker's workshop in Pittsburgh to get a new mounting before heading to South Africa. John Stefanos Paraskevopoulos, I always have trouble with his name, so I apologize if I'm mispronouncing it. In fact, his friends and locals called him Paris for short, and I may stick with that. He was Harvard's director of Arequipa since 1923, and then was selected to become the new director in South Africa. And he served until 1951. He reached Bloemfontein in July and selected a site for the new Boyden Station at the summit of a hill or kopje in Maselpoort, 14 miles northeast of Bloemfontein. In this task, he was assisted by the superintendent of the Detroit Observatory's Southern Station in Bloemfontein. The city of Bloemfontein generously helped by building roads, providing water, electrical and telephone lines, and offering engineering services, and also helped financially to the extent of several $1,000s. And here you see some of the early instruments from Arequipa being hauled by teams of oxen. Seems rather precarious, but it worked. And as observatory staffing increased, the Water and Light Department of the city of Bloemfontein housed unmarried assistants in shacks they owned at the foot of Harvard Kopie. These were described by Shapley as unsatisfactory, but Harvard lacked funds to build them a proper residence, and in 1932, Bloemfontein was not in an economic position to build Harvard housing on spec. The Bruce 24-inch photographic tablet had served Harvard well in Arequipa as its most powerful instrument for studying nebulae and variable stars. And on its new improved mounting, which you see being built here, it would turn its attention to the proper motions and structures of stars in the sun's neighborhood and to survey extragalactic spiral galaxies. Photographic plates of the southern sky would be compared with southern sky plates taken in Peru 20 plus years earlier. By 1932, Shapley had already counted 76,000 galaxies brighter than the 18th magnitude in just a third of the southern sky. Becker also made a new mounting for the Metcalf 10-inch triplet, which was to study faint variable stars in the southern Milky Way. And the last to leave Pittsburgh was the mirror and mount for the 60-inch Rockefeller reflector. This mirror had originally been made by Andrew Ainsley Common in England in 1885 and was refigured around 1927 in preparation for this relocation. It had originally been in use in Cambridge. The instrument had both a Newtonian and Cassegrain focus. The mounting was to be a two-pier English equatorial type and was set partially below ground in order to escape the wind. And I'll show you a picture in a moment. The turret in 1931 was made by a Johannesburg factory of Hubert Davies and Company, and then covered by redwood shipped all the way from San Francisco. The electrical driven platform, which was a novel design, was made by the General Electric Company's Riverworks in Westland, Massachusetts. Garish, the astronomer and engineer at Harvard, designed the trucks, truck wheels, turning gears, and so forth. And these were fabricated in Cambridge. So you have a whole collection of stuff coming together, being made in different parts of the world, and then being put together down in Bloemfontein. I have a brief but somewhat fun little construction sequence that to show. So here is the steam trucks with crates and workers coming. Then you see on the upper left the cage-like tube of the Rockefeller being unloaded and other parts in crates. Here we have, you can see surveying instruments being used to help lay out and excavate the spot for the foundation. And then the foundation is built and the turret is put up and topped off with the US flag. On the left is the new observers platform, and the right, the lowering of the polar axis onto the two parts of the mount. Here you see the polar axis on the piers below ground, and then the turret getting ready for cladding with the redwood planks. And voila, the whole instrument is complete. Now, this beast was the largest telescope in South Africa and the Southern Hemisphere for 15 years. Shapley planned to dedicate it to analyzing the spectra of southern nebulae, the velocities of bright stars, the light curves of faint variable stars, and the structure of the Magellanic Clouds, and he wanted to establish a standard series of magnitudes. But the common mirror was very thin, only 3.5 inches thick, and its rear surface was not flat. In fact, it kind of rocked in itself, and it required a nightly hack to overcome its astigmatism. So before taking a photograph, Dr. Paris would bend the mirror into shape by using pressure pads, counterweights, levers that were operated from the Newtonian focus. A new cell was made in the mid-1960s, but it didn't solve the problem. And finally, in 1968, better glass replaced the old common mirror. Already on site was the 13-inch Boyden telescope by Alvin Clark, which was devoted to planetary studies and spectrophotometry, and the 8-inch Beige photographic telescope. That latter, the Beige telescope, had already had 40 years of service at this time and had the record for the most photographs taken by a single instrument, 55,000 plates. 5 minutes, okay. In Arequipa, its spectrum plates had made possible the classification of southern stars. In South Africa, it would be used for studies of standard magnitudes and variable stars. And then there was also a new 3-inch Ross-Becker lens for a wide field patrol camera, which covered an area about 30 degrees and captured stars to the 13th magnitude. Now, Shapley called this a 3-inch policeman that was on duty to patrol all of the southern sky. The smaller instruments were placed in buildings with roll-off roofs, like you see here. The 60-inch had a turret, though, and one was planned for the 13-inch, but never built. The new buildings, Shapley remarked, were, quote, in architectural style, admirably suited to the landscape of Harvard Copy. Flat, square, and of white stucco exterior, they had what he called a very modern appearance. It's like mid-century modern, overlooking the wide plain below through which snaked the Mulder River. Although in partial operation earlier, Boyden Station was officially dedicated in 1933. And this aerial view shows the various instrument buildings and some still under construction. Now, by this time, Harvard also established its Oak Ridge Observatory in Harvard, Massachusetts, and had transferred from Cambridge its patrol cameras and other photographic telescopes. And when fully set up, it would have as many instruments photographically as Boyden. Harvard had Becker also build a second 60-inch reflector modeled on the Rockefeller telescope, but having a fork mount. And this was also equipped with a common mirror, which was then replaced. But this much earlier in 1938 by Pyrex glass. So the Wyeth telescope, as this was known, was the northern companion to the Rockefeller, and together they were going to make detailed photographs of spiral nebulae and globular clusters. Thus, the instruments at the two stations were twinned to give comparable results to northern and southern hemispheres. When the 24-33-inch Jewett-Schmidt telescope was installed in 1942 at Oak Ridge, Harvard planned a larger example for Bloemfontein, and this was the Schmidt modified by James Baker of 33-inch aperture and was known as the Baker-Schmidt telescope by Perkin and Elmer, built in 1949. And when it was set up at Bloemfontein in 1950, it became known as the Arma Dunsig Harvard ADH telescope. Similarly, Harvard set up new Damon patrol cameras at Oak Ridge in 1961 and paired them with identical ones at Boyden in 1970. So the Harvard, just to wrap this up, Harvard followed this course set in Peru, which it had found very satisfactory. Directions for research were made in Cambridge. The photographic plates were taken in both hemispheres and developed, and then they were shipped back to Cambridge for analysis and filing in the plate stacks. As Southern Instruments went, like the Bruce telescope, went out of service, they too made the long trip home to Massachusetts. And after years of storage at Oak Ridge Observatory, scattered here and there, many have now become part of Harvard's collection of historical scientific instruments. We've already heard about the significant scientific results of Boyden Station in the previous talk, so I will jump over that. But one thing that deserves to be mentioned is in 1955, Boyden became managed by an international consortium of the United States, Ireland, Northern Ireland, Belgium, Sweden, and Germany. And this Boyden International Council made Boyden Observatory the first international observatory in the world. In 1976, the University of the Free State took charge. So as I hope I've shown, it was no small feat to set up and operate an observatory and then relocate it to somewhere else and improve on it. And each of these steps came with challenges, both natural like weather and social challenges, which could be, new partnerships and politics between local governments and American and then international astronomers. So I'm going to stop here, but that hope gives you a flavor of the history of Boyden.
Thank you very much, Sarah. I think that there is no time for a question. Maybe we can use the coffee break for. I've seen that maybe, I don't know, if it is just a short.
Steve, I know, very interesting talk. Just a bit about the history of the international side. The Armagh Dunsink Harbour Telescope was also the first time the two governments in Ireland had come together to do anything together. So there's a very interesting international dimension, which I'm happy to tell you about later on if you want to know more about that.
I think it's a wonderful thing that, that's one of the opportunities of what can be sometimes seen as astronomical colonialism, but it comes with the prospect of sharing and development, collaboration. So there's a lot of good.
Thank you again. And now I invite Chris Sterkel and for his talk on the Leiden plate collection. Thank you very much. Please.
Thank you. Well, Leiden Observatory has an amazingly interesting collection of astrophotographic plates which have been collected over many years by many different instruments. But before getting to the plates themselves, I want to introduce George Phillips Bond, who in 1856 recommended to switch over from visual observing to photographic work. And Bond was very, very optimistic, as many people were. And he said, in place of the vague and uncertain estimates to which astronomers have hitherto resorted in attempting to express with numbers the relative brightness of the different stars, the magnitudes, they should use astrophotographic approach because, and there he gives a number of reasons which are very logic. The system is less liable to be affected by individual peculiarities of vision. There is less room for discordance between different observers. There is less room for disagreement between the conclusions of the same observer at different times. Yes, because this is a very important point, the third point, especially with visual observations when the observer ages. It's very difficult to combine the old data with the new ones. And lastly, this is overly optimistic that the photographic method, the approach, will eliminate the biggest problem, and that's the problem of color. And actually, this is not true, as we have already heard today. Now, the Leiden archive, with which I don't work in Leiden, I was just collaborating with people in Leiden, and I was introduced to the archive a couple of years ago, It has about 37,000 plates. And in 1897, they obtained one of the Carte du Ciel astrographs, I mean, one of the prototypes. And 1924, they had the double astrograph camera. Then came the Franklin Adams telescope to Johannesburg and in Hartbeespoort, where the Leiden Observatory Station is. Then a Rockefeller telescope, and finally Yale telescope. And they have also a collection of a couple of thousand plates from several parts in the world. And at this moment, about 1,000 plates from the collection is in other places, for example, in Brussels and others. So the Leiden astrograph, and I'm going to go very quickly over because you have heard the specifications of the Carte du Ciel telescope already in several presentations. And here you see the one in Leiden on the left side. And then I show also the one in Shanghai. These are the two telescopes which you don't see in the lists of participants of the Carte du Ciel, the list that Iliana showed. And the reasons for that is that the Leiden telescope, as I have understood, came a bit too late, but also they wanted to use it for other things, not just the Carte du Ciel, but other things. And this was, of course, a very wide decision. And the Franklin Adams telescope here, you see the system in a design. It came in 1902 to the Royal Observatory, where John Franklin Adams observed, and actually he had a very frail health. And what he did was really heroic. He would observe during the dark nights, and during the moonlit nights, he would spend his time in a sanatorium because of his health. This was really the hard way of working. So the telescope then moved to Transvaal Observatory, that became later the Union and Republic Observatory. And they made the Franklin Adams survey with this relatively small size telescope. And now I got several months ago from Alex Jamieson the news that they are rescuing the plates, that they also are rescuing the logbooks and so on. Now, the Franklin Adams Sky Surveyor, actually, when I was a young PhD student in Chile, we had on La Silla no access to atlases, photographic atlases, except the Franklin Adams charts. So we had to copy finding charts out of that for use at the smaller telescopes in the first place. So here you see the Dutch, the Leiden observing station, Hartbeespoort. On the left side, you have the Rockefeller twin astrograph. And on the right side, you have the Walraven light collector. It was the 90 centimeter telescope designed by Walraven, actually by Theodor Walraven and his wife. This is often forgotten, but she was one of the driving forces behind the design of the 7-band simultaneous photometer attached to the telescope. So the telescope was a long time in Leiden Station, and then it was moved actually to Chile. Here you see what we call the first day of the Dutch in 1979, and the young man standing behind the telescope is Jan Lapp, who went to Chile and installed the telescope, and it has been functioning there for about 2 decades. About 20 years later, they decided to close it, and the person who had the honor to do that, the last night of the Dutch, was a very symbolic date, April 1, 1999. In the morning, my PhD student came in the dome and to comfort me and to take a picture of the telescope that was put out of operation. The telescope has been used for a lot of science because if you use a small telescope, you have to be modest with your programs, but you can get an enormous amount of observing time because the big shots don't use a small telescope. Yes. And we used it for student training. We have had several Dutch students mainly coming to Chile and receiving training on that telescope. Now, we went through the logbooks of the Franklin Adams fields of Leiden, and here you see the distribution of the fields. There's a number of fields, and they all follow, of course, the Milky Way, with the exception of large and small Magellanic Clouds and a couple of other ones. So if you look in the logbooks, you can really reconstruct the scientific interest and motivation of the people who ordered these plates. Many of these people would never go there and observe. They had service observers. And the names of these service observers you can only find if you go into these logbooks. Now, we've heard this morning about the scanning project that you need to do a lot of effort for calibration and standardization. If you look at these plates there, these are the fields that have been used all the time for standardization. It's not the same. Standardization and calibration are two different things. And you can see that the fields here are evenly distributed in right ascension, but only in 2 or 3 cases they coincide with the field that you observe in the sky. And this is a defect, in fact, because if you move the telescope, even from east to west, the flexure and the telescope and the plate scale and a lot of things change. You have the refraction also. So if you take a standard here and you observe your object there, you have a problem, yes? So recalibration of a plate, and this is the plate which was taken here in South Africa, SAO, and the central star that you see there is an extreme supergiant star. It's AG Carina, and it has surrounding nebula. And on the left and the right, you see a number of spots, and these are the spots that remind you of the image that you saw this morning about the scanning machine. These are the spot sensitometers. So here you get a calibration simultaneous with your science image. And this is a very important thing because there are a lot of parameters during observation that you cannot recover if you look at these plates, say 50 years later or even a longer time. And by scanning these spots, you know exactly in advance by the construction of the sensitometer how the relative intensity of the light is. And by scanning these spots, you can calibrate the plate. And this is something that is absent in most collections, yes. So if I look to these plates again, you have 37,000 plates, which means 37,000 detectors, yes. You can subdivide these detectors in a couple of classes, perhaps 20, 25 emulsions types, but you often don't know which emulsion, and often you cannot find the specification of the emulsion unless the observatory has conserved these data. Then the primary detector, as we know very well, is nonlinear, the photographic plate. I mean, if you expose long, or if you expose, let's say, bright stars, you get saturation. If you have faint stars, they are lost in the plate fog. So this is nonlinear. The secondary detector is your scanner. And the secondary detector, of course, is linear. This is what we all try. Now, Leiden has tried to build a scanner themselves many years ago, decades ago. This was the Astroscan. And then they decided to build a second Astroscan. And actually, the project has been abandoned for I don't know what reasons. But I found a very interesting reference by Erik Deul from Leiden, who was at the design of the scanner. And he said the aim of the scanner is to get every bit of information in the correct way out of the plate. And then he gives an advice that is often forgotten. And the advice is that full understanding of the machine characteristics of the scanner is required to extract every bit of information from the plate. This is something that is forgotten. People, you can imagine you have a scanner, a flatbed scanner, you put a plate on it, you get an image, with the mouse you play a bit, and then you have your data. This doesn't work. You have to get deep knowledge about the scanner, and I think it is a very good point that was made by a colleague from Shanghai, how much care you do and time you spend really to understand the machine and to calibrate this. So these are the Leiden Rockefeller logbook. It's a copy, hand copied. The original is probably in South Africa somewhere. The copies are in Leiden. I went through a few of these. What you see there on the left side are the fields, on the right side you have the times and so on, and the names of the observers. And here you see observers, the Sitter, Wesseling, Hersprung, Van Hand, and Martin. What else do you find? That's logic. In this book, you find immersion, yes? You find the plate size, the plate scale, the observer, the filters, clouds, moon, interruptions, whatever, east-west position, exposure time, observer weight. That means that some observers are just better than others and more careful than others. And we call this observer weight. And observers who know each other know that this fellow is better than another one, yes? And very important, the clock correction. It's not in the book, but there is something in the book that allows you to calibrate the clock, because the clock depends on the temperature. I mean, especially in the past, the pendulum clocks, but also other mechanical clocks go with temperature. And we seem to have forgotten that temperature control in observatory domes was not there all the time. And look at this picture here. This is the temperature at Munich Observatory from about 1960 to 2005. And I have data before that time. And this it was a very expensive, a very precise Riefler pendulum clock, which was standing not just in the sunshine or no, in a vault, which more or less constant temperature. And you can see that until the moment of installation of the temperature control of the air conditioning, until then, you had a fluctuation, yes? And this fluctuation in temperature is there, and it affects your immersion and the response of the immersion. So it is a very important point, yes. So this is also from Alex Jamieson, a logbook from the Wits University. And this I found in the archive here in Cape Town at the SAO. These are notes which give you immersion type and a lot of information. So very often you get plates, but you don't get this information. And this should be preserved, it should be digitized, it should be made online available. So once you have your magnitudes, you have to be very careful. And I have here an interesting case of a BE star. And you see a time series of magnitudes. And when this very first magnitude has a large error mark. And why is this? Because it's a visual magnitude, but not visual. It is extracted for the Henry Draper catalog. And then the other data are, let's say, measured either photographically or photomultiplier. And the last one there is the very first space measurement by the IUV of that star. And what do you see? You see a few outliers, and you can conclude that probably the star is variable, is going into in outbursts or whatever. Now, if you add all the data that are in the catalogs, then you get this image. And again, the star behaves very strangely. But if you look at this series over there, these are all obtained by ground-based automatic telescopes. So no human, and with linear detectors, yes? Nice. But if you start to calibrate that, this is the result, because there is a 0-point error, yes? So this means the first measurement has no value in this, and then the IUV value is also very suspicious. When you look at the light curve over several decades, you come to the conclusion that there is just no variability at all. So this is just a list of different detectors that played in this graph which I have shown. So visual estimates from the past, combining them with data you extract either from catalogs or from photographic plates, you have to do that with be very, very careful. Now, SAO had a very famous standardizer, it's Alan Cousins, and I've met Alan a couple of times. And he told me in 2001, he told me just that he has always been unhappy all his life with photometry. And he was the only one I know who understood it and who built catalogs, who standardized. And he was mainly unhappy with the things that he did himself. And then he said something else. He was not looking happy. And he said, I could never agree with the Dutch guy, the one with the short name. I cannot recall the name. I know only two colleagues with a very short Dutch name. So I tried first, and I asked, was it Lup? He said, no, it was Pell. Yes. Jan Willem Pell resided a long time in South Africa, did very good work on Cepheids. I'm going to mention this in another talk later, but Jan Willem Pell has done very useful work at the Dutch state. Again, the archive, I have made just a diagram here where you see on the horizontal axis the plate scale, on the vertical axis the sorry, it's the scale on the vertical axis and the arc seconds on the horizontal, and you see for every of the Leiden plate samples, you see their position. So actually here, this is not a photographic, the one up there is not a photographic, this is the Walraven telescope, but with a CCD camera, yes? So it has a very small field, but it has a very high plate scale. If you're on the lower side here, you have the reverse situation. So actually some of the best plates are somewhere in the middle there. I have just an example here, and it's from the Rockefeller telescope. I have no access to the plate. It is somewhere in the Leiden collection, but I received the print, which was probably prepared for a publication. And this is from the Small Magellanic Cloud, and the arrow points to a Wolf-Rayet star. It's a very interesting Wolf-Rayet star. It's a binary, it's a very eccentric binary. It has a period of 20 days. And on top of that, it has a pulsation period of about 6 or 7 hours. Now, if you go to one of the plate samples, which is a very crowded plate, you get this image. You can imagine that analyzing this image in an automatic way can deliver you data which may not be very reliable. That's another plate, another photographic plate. This is a lot better. You probably can extract useful information from the parts from such an image. And this one is the Dutch telescope, the Walraven telescope with a CCD frame. So you pay because you have a very small field, but you gain because you have a good resolution and actually a good quality. Let's look now at the observers, and I was very impressed by seeing that this fellow, Chris Martin, was observing also very intensively. And here you see that he has taken 250 plates in several months. Almost every night that he was available, yes. She died in 1945, not in South Africa, but in Indonesia. And why was that? Because she left South Africa to accompany his supervisor, the sitter, to Bandung, to Indonesia, to Bosha Observatory. And these were war times. He ended up in a prisoner camp, and he, like many other young people there, he didn't survive it, yes. This is a fellow with an extremely high observer weight. Everything that he did was well done, and moreover, it was done in the independent way. He was a silent man, did a very good job, and this is something which is not in the logbooks. It is by Jan Oort in 1946, he published an obituary about Chris Martin. Yes. So here from the logbook, you have the other observers. There is a fellow there, Hendrik van Hand, who was observing minor planets, discovering minor planets, and he started a tradition to name minor planets, to his colleagues who were all working here in South Africa. Then, Obituary of Van Hent is a very nice statement about the task of the Leiden observers. The task was a bit romantically expressed, like the astronomical mine worker who is extracting the diamonds, and then the diamonds have later to be polished into jewels. Yes, this is a very nice way to tell, but also the polishing into jewels in our terminology takes a lot of work. What about the future of the archive? Well, in 1944, they moved the entire archive to a bunker somewhere in the dunes to protect them from war damage. Then the archive moved back to Leiden, but there were some problems with humidity, there were problems with water, and so on. Then they were moved to the Huygens lab, and now there are plans to store all the plates in a storage place in the Boerhaven Museum in Leiden, but this plan is not really effective yet. So what should happen, I think, is that Leiden should request that the plates that are a little bit everywhere return. They should also perhaps return plates that are not belonging to them. They should digitize the logbooks and observing logs, make the logbooks and the observing schedules and information open access, accessible to everybody. Then very important, decide on a digitization project. And perhaps we should get together in a conference specifically on this. So I wish to finish with another optimist, and this is George Eastman. If you can satisfy an astronomer, you can satisfy anyone. He looks very satisfied because he made a lot of money because of us. But if people like Cousins are not satisfied, it's going to be very, very difficult to get what he wants. Thank you.
Thank you, Chris. So there is time for questions, but maybe there are also questions from the Zoom connected people. So first, of course, if there are questions here in the hall, please. First.
Thank you for your Okay, thank you for your excellent presentation. You showed us the caveat on the long-term trend of the cross-plate data and what kind of way to calibrate such inhomogeneity, which you showed for the let's say the fake long-term trend, which was shown in the cross-plate data. No, in the latter half.
Oh, it's done. Well, I can.
Okay, we can discuss this later. Yeah.
Okay.
Thank you for your quite good exposition. It's considered to send a request for UNESCO to this plate collection will be recognized as memory of world.
We have not discussed this possibility because sorry. We have not discussed this possibility because the situation right now is that the plates exist somewhere and there are very few people who are worried about what will happen with them. Yes. So we should get together with a number of people and discuss this possibility also.
It could be the occasion to return to original place.
Oh yeah, sure. I think one should return the plates to where they come from and keep all the information together.
Thank you, Chris. Is there any question from? Okay.
I'm afraid I'm a terrible skeptic about the value of plate collections. And I'm quite interested to hear if you think the use that's made of them has been enough reward for the huge amount of intellectual effort that's gone into preserving them and cataloging them and so on.
I didn't get.
Sorry, I mean, bluntly, what use is it to save plates on long term? Have people made use of these collections? And if so, more or less, how have they made use of them?
Collections of in general, the selection as scientific information can be extracted some kind of scientific use of these collections.
You're right, and the skepticism has been expressed, I think, on the online conference that was organized by Dr. Tang a couple of weeks ago in Shanghai, that some people think that actually it's a lot of work and a lot of effort for very little outcome. Yes. But this is the price we have to pay. I believe useful information can come out, but we should not lose our time by mass producing numbers and just publishing things which make no sense.
Okay, thank you. Just let me check if are there questions from the connected people for the different speakers, of course, not only for it. No, it's okay. Perfect. Thank you very much. So I think that is there any other comment or question for also for the other speakers of this session? No. Thank you to the speakers, and I think that we can stop here for the moment, and we have the coffee break from half an hour, and we have to be back here at 15:30. Thank you very much to everybody.
I'm at a find you do, and I go use it, and I'm hello. Finally, I find way to talk to the girl, but she don't follow. You done it, bum, bum, bum. Why you know I come from? You know, bum, bum, bum. But she give me some strong one. I know she must sit down, I want you. But she really say, don't want, cause I'm friends with my like Jim, don't want. But they come on like Jim, don't want.
This hotel card has been found. If anybody knows who lost it, or one of you lost it, says Onyx on it. Anyway. So the first, this session is about the Royal Observatory, Cape of Good Hope. And you probably all know Virginia Trimble isn't well at the moment. And so Chris has offered to essentially reconstruct her talk and talk about what she would have talked about. So Chris, please go ahead.
Well, unfortunately, it's about a week ago when I received the list of participants. I used to check if all my speakers are there. And Virginia was registered since a long time and told me she had paid and so on. And she was cancelled, yes. Nobody told me. Then fortunately, since Virginia does not use too many computerized systems, I had to help her a lot. And I was in contact with her secretary, so I asked the secretary what happened, and it seems that Virginia is very ill and she was in hospital. But her talk was cancelled, and this was unacceptable to us, I think, because if the presentation is cancelled, it's also cancelled in the proceedings. And we shouldn't do that because she could be back, hopefully, in a couple of weeks. And this is why I have reconstructed the talk on the basis only of her abstract, which is very short, but anyway. So it's about expanding the universe from South and Southern Africa. And expanding the universe means actually more or less the doubling of the image we had of the universe in the 1950s. Now, in our talks tomorrow, we are dealing with triangulation and surveying of South Africa and of the Cape. So I just like to start with the idea of triangulation. Actually, one of the very first diagrams on triangulation is coming from Hemma Frisius, who explains here how you calculate the distance to a point that you cannot access. And the very important thing is, first of all, you construct a baseline. And this is here going from Brussels to Antwerp. I'm showing here the baseline. And the baseline is crucial because the baseline for terrestrial measurements has to be measured with extreme accuracy. Because if you make an error there or inaccurate measurement, your distances are wrong, yes? So once you have a baseline, then you measure a triangle, not any triangle. It should be a triangle that looks a little bit like this. You should not have a very skew one. And with these calculations, you know the distance. This is a principle that you know very well. And so let's go to the very first stellar parallax. And this is a textbook that says that Bessel, as we have heard, was the first to publish parallax of 61 Cygni. And you have the diagram there in the presentation in 1898. 61 Cygni is a binary. And here I just show you two positions of the star. This is you have the star over there, and then 50 years later, it is on the left side there. So it's quite a distance that the star is moving. The proper motion is large. This means that you can assume that the star is relatively close, yes. So how do the measurements go? You measure the position of the star relative to background stars. And you can see here on the diagram the fluctuation in the orbital motion of the Earth, which is reflected. This is a reconstruction of the old data reanalyzed by the authors which are mentioned here. So every measurement has a reasonable error bar, and the analysis yields the distance. Yes. Another case, as Jan Glass has shown us this morning, is Proxima Centauri. This image that I show you here is one of the very booklets that he has published about the history of Proxima Centauri. You can see here three images in three different bands. And this is the motion of Proxima Centauri. Proxima is really the closest star to Earth. Yes. It's very quick. There was some damage to the mural circle when the mural circle came to Cape Town. In unloading from the ship, it was damaged. It has several problems. The graduated circle was not really a circle. The center of the circle was not very well centered. The pivot was not really perfect. So apparently, Fearon Farlows in the beginning was very discouraged. But at the end, by measuring all the microscopes and making a weighted mean, you could do good measurements. And Henderson started to undertake measurements of Alpha Centauri to determine the parallax. He carried out the first measurement, but actually he delayed publication, and Henderson came to the Cape, but actually he did not really want to do that. He preferred a job in the UK, but he didn't get the job, came to the Cape, was very unhappy there, and actually he left the Cape just like this after 14 months, even without waiting on his successor, who was Thomas McClear. So in his comments, he talked about the dismal swamp, because that was the epithet used for the place where the observatory has been constructed. Here you see the parallax measurements of some nearby stars. You have Alpha Centauri up there, and then Proxima Centauri, and then 61 Cygni Alpha Lyrae. And the blue dots are the modern measurements based on space measurements, Hubble Space Telescope, Hipparcos, and so on. You can see that for several of them, the agreement is quite good. Of course, the error bars on the left are error bars of the measurements. The error bars on the right are smaller than the symbol. Yes. So, and this is the advantage, of course, of space-based observations. Now, if you wish to go further, you can measure only 4 or 5 nearby stars by the classical parallax method. You need a longer baseline, and the longest baseline that you can have is the diameter of the Earth's orbit. And if you go into space, you can extend that a bit. So you need another baseline, and a material baseline is not possible. Fortunately, we had a discovery by this young lady, Henrietta Levy, who found out that the periods of the Cepheids, pulsating stars, correlated very well with their absolute magnitude. And talking about Cepheids, here you see a light curve of light and color curves of Cepheids. They were made by Jan Willem Pell from Groningen. Pell, whom Cousins had problems to get agreeing to it, but Jan Willem Pell made measurements of 150 Cepheids in the 1970s from the Dutch station, from the Leiden station in South Africa. So all you have to do actually is determine a couple of these light curves, take the difference between two maxima or the difference between two minima or many others, determine the period, then plug it in a diagram like the one you see here, which Ms. Leavitt has published, and then you get the absolute magnitude. And from the absolute magnitude, you determine the distance. Of course, you have to be very careful. The model that you accept for the universe can be wrong. For example, when Lacaille came to the Cape to measure the length of the degree of a meridian, the model he had was a perfect model of the geoid. Yes, and it didn't work. Yes, the model was wrong. Here also, if you get the absolute magnitude, your model assumes that there is no interstellar absorption, there's no reddening. Yes, so if the model is wrong, you get into trouble. That's absolutely relatively simple method. Now, Virginia wrote, she's been writing me several emails in the last few months, and she was all very encouraging about what we were preparing. And here you see one of the mails where she actually politely complains about a statement in a current Sky and Telescope where people are informed about the situation in the 1950s, where a fellow stood up at the General Assembly in 1952 and said something. And the fellow, of course, is South African, very famous. And here you have the key players of that moment. And this was Walter Baade, then Thackeray in the middle, and then there is Shapley over there. September 1952, AU General Assembly gathered in Rome, and there was a large amount of people there, 430, yes. Compared to what we are doing today, this is quite a difference. Baade used the 100-inch telescope on Mount Wilson. David Thackeray had the 74-inch here in South Africa. That was then the largest telescope in the Southern Hemisphere. And Shapley was using the 24-inch blues, and now we come back at Boyden Station near Bloemfontein. Now, the discussion was that Baade could not detect the pulsating, the earlier variables in M31 in the Andromeda galaxy with the large Palomar telescope, yes. And then Thackeray just stood up live in the meeting and said, yeah, but I have seen that in the Magellanic Clouds, yes. And that was kind of revolutionary, really a shock. The shock was like this, that even in the New York Times, was a publication, I can't show you a readable one because I have to pay for that, but this is this is the screen image, but the content I have. And Shapley, New York Times writes that Harlow Shapley is announcing that the size of the universe is doubling, and he's of course talking only about himself, and nobody is just mentioning David Thackeray. And this is actually the message that Virginia wanted to bring. That is not really the fair way to work. And then she jumps, of course, to the consequences for the Hubble constant. Hubble constant at the beginning, when it was determined, was of the order of 500 kilometers per second and per megaparsec. And then by Thackeray and Baade in 52, it went down to 280. And finally, the current value is about 68 to 70, 75, yes. And this led Virginia, some time ago, to publish a paper about the variable constant, the shrinking constant, yes. So this is about the message that she wanted to bring here. And besides that, in her talk, this has a couple of sidelights. And here you see the top line says 3 G's for the southern sky, Thackeray, Feast, and the extragalactic distance anomaly. This was the very first version of the title of her talk, yes. But this happened to many other people. They send something and they send an abstract, and then afterwards, when they start working on it, they change it. So this is the original title, Cheers for the Southern Sky. Yes. And she has sidelights, and one of them is here, somebody I never heard about. This is Samuel Okoye, who was a Nigerian radio astronomer, and actually the very first astrophysicist Black African to obtain a PhD in radio astronomy. This is one of her 2 sidelights. And the second sidelight is Michael Feast. I don't know exactly what she wanted to say, but certainly the importance and the contribution of Feast in the field of Cepheids and the extragalactic distance determination. And this is about all I could take out of the abstract to tell you. However, about Feast, I would like to add one sidelight of myself, if I may. And 25 years ago, I went for the first time to a conference about the history of astronomy. Yes. And the person I met when I entered the meeting room of that place was Michael Feast. It was a conference in Groningen. These are the proceedings prepared by Piet van der Kruijt and his colleague. I came into the room and Michael Feast came in from the other side. He shouted at me, and he shouted. And those who have known Feast know what it means, shrieking. You are too young to be here. Yes. He was joking, of course, yes. He was joking. And actually, this is one of the problems we have. People who are doing history of astronomy can do this only if you are not a professional historian. Can only do this when they get a bit older. They can relax a little bit in the field work and spend time there. Yes, so it's one of the problems. We get into this field of research at later age and with less funding. Yes, and this is why also some of us here had problems to get here, and some of us can't get here because they don't get the funding. Yes. And the second problem we have is so well expressed by Virginia in one of her mails, and I show it here. Another problem, she said, if I manage to get there, I don't remember the date, but it's a couple of months ago, at 880 and not a close relative of Kissinger, I can be sure of participation. Yes. So that's the second problem we have in this field of research. So this is all I can tell about what she wanted. But the last statement is actually, I can bring, I think, the spirit of Virginia in this room by showing this. Yes. And let's say we hope she's getting better. And we are going to pass to everybody a little booklet and ask anyone who wants to send her a word to sign this. Thank you.
Anyway, if people have got any comments or questions for Chris, now's the time. Yeah, Dave Laney. Maybe, oh, no, he's coming. It's like, oh, yeah.
This is a very minor point, but as far as I know, the biggest problem with the mural circle that Fallows and Henderson and McClear tried to use was that the pivot had not been attached with anything but soft solder. And so it simply wobbled in a very curious way, such that Airy found himself totally unable to understand what on earth could be going on. And no one did until they took it apart. As far as anyone can tell, Jones probably was having somebody else do the pivot, and somebody, while his back was turned, they had decided that we'll do this in a really short, simple way and save some time.
You can comment. As I understand it, McClear and Henderson eventually analyzed what results they were getting by averaging all 6 of the microscopes used to read the circle, and found that the average behaved perfectly well. But it's perfectly true what you say. When they took it apart, they found that the soldering was very poor.
Heat shrinking the thing onto the shaft, which would obviously be just a bit more stable.
Okay, yes, please. Yes, that
Who was the maker of the mural circle?
it was Jones, who was one of the instrument makers around that time, Troughton and various others. But I think Jones had actually trained under Troughton. Yes, there's.
Thanks. It's not really a question, Chris, but Virginia's sidelight note about Sam Okoye. Sam was a PhD student in astronomy in Cambridge, and he will briefly have overlapped with Virginia when she was there as a postdoc. So Sam went back to Nigeria and had imminent career as a teacher, that he was indeed the first West African radio astronomy student that I know of, certainly in Cambridge. We have a great big poster of him on our wall with that information under it.
Have we any more comments? Here's one over here, please.
Thank you, Christian. You did a good job for Virginia. This is the second year I have missed her, once in America and now here. So I'll be signing the book. I just wanted to ask on one of her side issues with regards to historians of astronomy being a little bit grey-haired and all the rest of it. Do you think that this is a problem that can be addressed where we can get younger people coming up through the ranks to actually think about careers of history of science, history of astronomy?
Well, in Commission C3, in Commission C3, History of Astronomy, we are trying to attract younger people and also to attract people with a formation either in archiving or in history of astronomy. The reality at this very moment, I made the calculation, is the median age of our scientific organizing committee and even some of the speakers is above 75. And this is why, of course, people, while they say, some people think that doing history means is looking backwards, and that has no value. The fact is, by looking backwards, you can discover the errors that are in the scientific method and use them to avoid looking forward in the future, yes. And some of these errors are mainly also errors in the conception of the model that you try to measure, yes. Because, for example, long before they doubled the size of the universe, Joel Stebbins came home and told his wife, hey, we shrank the universe. Because they discovered interstellar absorption and reddening, and then the universe became smaller, and then became bigger again, yes? So you have to adapt your model to reality, and knowing the past helps a bit with that.
Thank you.
I had an interesting conversation once with Donald Osterbrock, and he wrote the most fascinating books about the history of Lick and other places. But one of the problems is that astronomers write history from an astronomical point of view. Historians like going into all the little details, you know, the alleys that never led anywhere and so on. So they accuse astronomers of having a Whig view of history, as they called it. But I think there's a lot of room for both, because when you left it to historians, it'll probably get quite boring, actually. Yes. John Henshaw.
Just to add to those comments, I want to dispel the idea that history of astronomy is for old astronomers who want to look back. Actually, I think all astronomers, including the young ones starting out, should embrace the history of their subjects they're researching, because you can't do research in the current age without knowing what's been done before and how your work fits in with what was done previously. So I think it's essential for every starting out PhD student and postdoc in astronomy, they should get into the history of their subject. And that's vital. And I was very lucky, because when I was a postdoc in Paris, I started being interested in history, and I spent 5 sabbatical leaves, each one a year long, from the University of Canterbury, doing history and writing books. And in between, I had no time, because I was teaching students and lecturing and doing observing. But history and research should go together for everyone at all stages of their lives.
Yeah, thank you. Well, actually, the Division C days on Monday, Sarah Schechner, who is my successor as president of Commission C3, will also contribute a presentation about the value and the need for history of astronomy. It's a problem that we also have inside the division, but I cannot say too much about that.
May I have a
Any
query?
more comments or questions?
I'm
Well, I
speaking
think
virtually.
questions
Can I,
value
am I
making.
audible?
That's what Virginia had in her mind.
Am I,
Our next speaker is Dave Laney, who's going to talk about from the dismal swamp to SAAO. So he spent some time at SAAO, but it wasn't too much of a dismal swamp at that stage.
There we go. I must say I owe Ian a debt for having located this picture. I'm not quite sure where it was I found it, but somewhere online I found a whole treasure trove of stuff. Ian talked about having a big view of history. I suppose this would be the mud view of history. Astronomy in South Africa, as people have mentioned, started because people were trying to navigate by the stars. And things were quite exciting if you were sailing a ship and trying to use very primitive instruments to tell where you were. As was discovered, for example, by the Sanhua, or however you actually pronounce it, St. John the Baptist in English, which collided with the South African coastline in 1552. There were very few who actually survived the trek along the shore. Now, the early charts showing the southern sky were anything but accurate. And when Father Guy Tichard, who was mentioned earlier, visited Cape Town on his way to Siam, he found, among other things, that Cape Town was 300 kilometers west of its position on his maps, which would not have helped in avoiding the South African coastline. Many of the stars marked on his charts didn't even exist at the marked positions, and a lot of them that he could see were not there. This rather fanciful illustration has absolutely nothing to do with the way their observatory may have looked, but the artist was probably influenced by the fact that they were going to Siam, so he made it rather vaguely oriental. Now, Nicholas Louis de Lacaille, apart from being the only researcher I'm aware of who, after spending 2 years at the Cape on what essentially was a research grant, handed back the unused portion of his research grant to the enormous astonishment of the authorities involved. Now, he was using a 13.5 millimeter telescope. So while his positions were reasonably accurate, I found a recent study that indicated that the median accuracy of his star positions is about 0.3 arc minute, which is about twice as accurate as the positions by Flamsteed in Britain at the time. Now, he also decided to add 14 constellations so you could fill up the southern sky. Most of them are rather faint and obscure. Now, in 1820, the commissioners for discovering the longitude at sea, which was the big problem of the day, decided that they were going to establish an observatory at the Cape of Good Hope for the improvement of practical astronomy and navigation, and to promote the glory of the British name. I like that part. It was supposed to have the same major instruments as Greenwich in England, and it really did get a 10-foot transit instrument and a 6-foot mural circle. And the astronomer was to have the same salary as the Astronomer Royal. There was only one problem. He didn't get the same staff, and as a result, things went very slowly. They were also supposed to have a zenith transit, but that never actually got built. Now,
Fearon Fallows' only image that we're aware of is this silhouette. He was a weaver's son who actually studied math books while at his father's loom, but his outstanding mathematical ability got him sponsored to Cambridge. And apparently, with a desire to please some of the people who had sponsored him, he had himself ordained in 1819. He also built a reflecting telescope, grinding the mirror himself. And one of the incentives may have been the fact that as a fellow, he couldn't marry, but as His Majesty's astronomer at the Cape of Good Hope, he could and did marry Mary Ann Hervey. Now, the instruments for the new observatory did arrive with Fallows, but I'm only talking about the temporary instruments, which were small and portable. But they arrived in Simonstown, which was 23 miles away from Cape Town, on such bad roads that Fallows didn't think his instruments would survive. So he had them sent around the Cape Peninsula by sea. And the colonial government decided that they didn't want to pay a penny of his expenses or a penny for anything else that he wanted, in spite of the fact that it was an official British government project. The only way that he escaped having his instruments dumped on the beach by the captain of the ship was because the president of the Burgher Senate, a Dutch gentleman as he describes it, found a room in the town granary which could be used to store the instruments while he found a place to use them. So in the garden of his rented house, he set up an 1820 settler's hut, which is the rightmost hut that you see in this old watercolor, and tried to use his somewhat damaged portable instruments to make observations. His clock was so bad that he had to invent methods that didn't need a good clock. And he had trouble because moths got into his telescope and destroyed the crosshairs. His landlord decided that Fallows was spending too much time looking down into his garden instead of up in the sky, so he had to move to a different rented house, which then apparently partially collapsed. He lost a lot of time because of illness due to the unaccustomed hot climate, which may be a surprise to those of you who are new to South Africa. This is, however, the middle of winter. But the real problem was that, like other early astronomers at the Cape, Fallows insisted on dressing as he would have done in Britain. And in heavy woolens, the Cape summer was not a friendly place. Anyway, he finally produced a catalog of bright southern stars, which got lost in the mail. Of course, Fallows had to find a place to put the new observatory and traveled every place he could think of for about 40 or 50 miles around. They had suggested Tiger Hill, to him before he left, but it was totally unsuitable. And Table Mountain was even worse, as anyone who's ever looked at the tablecloth clouds that hang over it would realize. But it was also a problem that most other sites had clouds of white sand or red dust blowing through them on a regular basis because the Cape was very windy. But he found a place between two streams, which was free of sand and dust because what the locals called Snake Hill, Slonkop, was in the middle of a swamp. And then for the next few years, absolutely nothing happened. The Admiralty lost the plans, then had them redrawn by an architect who had never designed anything that didn't have to do with harbors and canals and water, and who had no clue about observatories, best expressed by the fact that his telescope observing rooms under expensive, impractical copper domes had springy wooden floors, so that if you tried to observe anything, the stars would dance around and do a wonderful jig. He also lost their only child early in his stay at the Cape, and his wife had several miscarriages after that. It was not altogether fun. He also had a little bit of a problem with his assistants. James Ferrer, who he described as a lazy and insolent drunkard, married the Fallow's maid, Sarah Bootle. Sarah Bootle was just as prone to drink as Ferrer was, and often had to be carried upstairs to bed. So Ferrer became a watchmaker. His sister Betsy apparently had an unexpected event, as Fallows delicately put it, and ended up having to be hustled off to England. Patrick Scully had the same sort of problem from the other side. He was the first Catholic chaplain in the colony, but Fallows found him in his own house, having a really good time with the housemaid, who was the daughter of one of the local settlers, and got rid of him. The governor was very displeased because apparently standards for clergymen in the colony were exceptionally low at the time, and he was afraid he wouldn't end up with any if Fallows standards were applied. His next assistant did do one thing. The permanent instruments for the observatory arrived, and the mural circle suffered an accident while it was unloaded, which probably had nothing to do with its bad performance, although Fallows, Henderson, and McClure all thought it did. He doesn't seem to have done a great deal, as far as I can tell, while he was Fallows' assistant. But the person who did help Fallows a great deal was William Skiro. Now, Fallows did not know very much about building, and if he had been in charge of the building methods for the observatory, the building might not still be standing. But Skiro was an expert sent out from England to help him out. It apparently was rather exciting. Fallows often stayed in a tent on the grounds. And it was dangerous enough that a guard of 10 soldiers was the only thing that kept the tools and building materials from vanishing every night. And Skiro and Cannon, the contractor, were on the site after dark only with firearms and dogs because they felt they were in serious danger. Now, the building did not get built quite the way that they had planned it on the Admiralty back in England. It wasn't built of cut stone because there was only one really qualified stonemason in the colony. So they used rough stones, covered it with cement, painted it gray so it looked like the pictures made back in England. And it's that way to this day, complete with the wooden pillars around brick cores. Now, the huge heavy stones needed a special wagon that often broke down. And the biggest stone actually had to be moved across the landscape for 3 weeks because no wagon could possibly hold it. That took 2 years. In the meantime, Fallows had spent many years of his life now in the Cape, accomplishing rather little in terms of astronomy, and he was getting incredibly frustrated. Of course, there were other attractions to the site he had chosen. It wasn't called Snake Hill for nothing. 90 were killed in one day, many of them poisonous, and countless on other days. Leopards could appear. Supposedly, the odd hippo or two could still be seen in the local rivers. And then the new government in Britain cut the funding so that instead of having outbuildings, a bridge, a road, a water supply, anything unimportant like that, he had absolutely nothing. They suggest that he simply hang a bucket over a tree limb with a rope and get water out of an unlined well. That was, in fact, the only source of water other than bringing it in by wagon for many years. So, as Piazzi Smith was later to describe it, it was as though somebody had dropped this building out of the sky into the bare ground. The architect had never thought that toilets of some kind, even outhouses, might be needed. I love this statement. Great official people in London could not be troubled about such unpleasant things. The The mural circle gave inconsistent results unless you averaged all 6 microscopes, which slowed work down to a crawl. But the government had no intention of paying for a replacement, and if they'd sent the circle back for repair, it would have taken months each way. The winds were so fierce in the days before there were any trees on the site that it sometimes would strip off parts of the lead roof. Of course, while the scaffolding was still up, Fallows found one day that he couldn't open the shutters and climbed up the staircase onto the roof to see what the problem was. His problem had 4 legs, spots, and a tail, and he and the leopard left in opposite directions fairly rapidly. He felt especially unsafe after his guard of soldiers was withdrawn in 1829, which immediately resulted in the remaining building materials being stolen. And he felt that somebody was likely to throw stones at him from outside if the observing rooms were open to the sky. Now, 2 observers were necessary, one for the transit instrument and one for the mural circle. And after Captain Ronald left, his only assistant was Fallows' wife, who would operate the transit while Fallows operated the mural circle. Nobody could figure out what on earth was wrong with the mural circle, but they used it. And Mrs. Fallows discovered a comet in Octans. Other people, of course, had also discovered it in other places, but her independent discovery of comet 1831 was the first South African woman observer to find a comet for a very long time afterward. Now, he converted one of the rooms near where I used to have my office into the first Anglican chapel in South Africa and officiated every Sunday, performing the odd baptism and marriage. But time was running out. Less than 2 years after work began at what Henderson was to call the Dismal Swamp, Fallows became very ill with scarlet fever that developed into edema and jaundice, and in July 1831 died of fever and overwork. He's still buried in front of the observatory, 12 feet underground, even though there were no grave robbers or medical schools in the Cape. Why he felt that was necessary, we do not know. And of course, although his observations reached the Admiralty relatively quickly because Mary Ann wasn't about to let them get lost, it wasn't until 1851 that they were finally published. That's a picture of his grave. Now, in the meantime, Lieutenant Meadows arrived in 1831 and found that one wing of the observatory building was actually operated by a reverend and his wife, and the wife had leprosy, which probably was not a great encouragement. And Meadows and his wife were described later by McClear as the most croaking, hopeless couple he had ever encountered. They promptly took an exceedingly great dislike to their station at the Cape, and they composed this wonderful poem, which ends with "The slough of despond intercepts our main road, and near Dismal Swamp stands our stately abode." Well, that's a watercolor from a few years later, showing a little bit of what they meant. There was a swamp behind them, formed by the Black River. And if you wanted to get to Cape Town, you basically either had to wade or ride on horseback or in a wagon or a cart to get across the Liesbeek, which at some seasons was a sufficient barrier that the observatory seemed like an island in a hostile sea of wilderness. Now, when Thomas Henderson arrived the next year, Meadows and his wife promptly filled him full of snake stories. And he wrote to his successor about his residence in dismal swamp among slaves and savages with venomous deadly snakes, and how no one dared put down a foot in the warm season unless you were certain you weren't landing on a snake. It wasn't really quite as bad as that. Now, Henderson had distinguished himself in the law, and as a skilled and enthusiastic amateur astronomer, I might add that after Fallows, it would be quite some time before the authorities in England could find a professional astronomer to take up the post. He was a hard worker, in spite of the fact that he disliked the Cape so much. And he provided first a time service for ships in Table Bay by extinguishing an argand lamp at a set time. But then he brought a brass pistol, which is in the Observatory Museum, to give time signals by firing it at set times. I've seen photographs that show it produced an absolutely enormous cloud of smoke, so it would have been reasonably easy to spot from the ships in the bay 3 miles away. The picture on the lower right is actually a picture of a mural circle somewhat like the one that he used. Now, Henderson and Meadows really did an enormous amount of work, which was very good for the time, as accurate as the best observatories in the Northern Hemisphere. Now, Henderson was especially distinguished because he was very interested in systematic errors, and is the first one we know of, well, one of the first British astronomers to derive the probable error of his observations from theory. He got a good lunar parallax and started observing Alpha Centauri based on a letter from Manuel Johnson in St. Helena, as has been mentioned earlier. But when he got to Scotland, all he had in hand were the declination measurements. The right ascension measurements were sent to him later by Meadows, and although he could see just from the declinations that Alpha Centauri had a large parallax, he could not really derive an accurate parallax without the full set of data. And even when he had all of it, as Ian can attest, his error bars were considerably underestimated. He could really just say that Alpha Centauri had a considerable parallax, but it was pretty uncertain. Now, Henderson finally lost his patience completely in the middle of a dispute with the Admiralty about water closets, toilets, in other words, writing to the Admiralty on the subject of the conveniences in a deliberate but manly tone, and took the next ship for Britain, where he, with incredible good fortune, became the first astronomer royal for Scotland. Since he had very little income other than his salary at the Cape, that was a rather daring move. They couldn't get a Cambridge mathematician this time either, and the Cape Observatory didn't have the best reputation by this time, so the Admiralty sent another talented amateur astronomer who took a considerable cut in income to take up the post. Thomas Maclear was not impressed by Meadows' greeting about accepting this wretched appointment. In fact, he packed Meadows and his designing female servant off to England before very long, fired Ferrer, and tried to use his footman as an observing assistant. Unfortunately, his observing assistant was a reasonable artist, but totally hopeless at astronomy. The main contribution he made was producing a systematic error when the instrument came into contact with his head. Now, Herschel arrived at about the same time, as has been mentioned. One of the things that Maclear did was come up with an ingenious solution to the problem that the observatory was on a main cattle track, and as he put it, it was sometimes surrounded by cows trying to thrust their horns through the windows. But he had a trench dug, which was relatively inexpensive, always important with the Admiralty, planted with prickly pear and aloe. And trespassers had to keep their distance. He put up a time ball when the new commander in Simonstown appears to have wanted one. And he got an assistant who was 16 years old. Not everybody gets a position with what for that time was a substantial salary at 16. But Charles Piazzi Smith had the good fortune to be the son of Admiral Smith, who was a friend of McClure. He got to spend lots of snowy winters on mountaintops in the first geodetic surveys in South Africa. He also seems to have been instrumental in possibly saving McClure's life when McClure fell desperately ill and Smith actually ran to Cape Town to fetch a doctor through the swamp, presumably. Now, the most welcome visitor at the observatory by far was John Herschel, who set up his observatory a few kilometers south. And they wrote a lot of lively letters to each other, which were collected by Brian Warner, fortunately, and took a great interest in nebulae, Halley's Comet, the variation of Eta Carinae. And Piazzi Smith was working, for the most part, 18-hour days, and even McClure was worried that he might actually break Smith's health by having him work that hard. However, later on, there was more time for other things, and Piazzi Smith invented a new type of air conditioner at the top center, installed the first windmill-based irrigation system in South Africa. He actually succeeded in growing pineapples on the observatory site, which has certainly never happened since, and took the first photographs of any observatory as far as we know, and probably the first photographs in South Africa of anything. He was a reasonable artist, and he really was not very impressed when, at the appearance of the comet of 1843, he cleaned off the old Herschel 14-foot reflector and tried to measure its polarization. And McClure insisted that all of this had to be thrown out and they would just measure the position. Smith recorded it all in the observing book, much to McClure's annoyance. He had no interest whatsoever in his personal comfort. And McClure once said that he didn't really care if he dined on an old cow's tail. Smith then left the Cape because he had been made Astronomer Royal for Scotland after Henderson. This was becoming a tradition. And Piazzi Smith's most important contribution after he left the Cape was probably his experiment in 1856, where he went on a mountaintop in Tenerife and showed that seeing on top of the mountain and the visibility of faint stars were enormously greater than they were at the observatory in Edinburgh. That central picture shows a double star as it appeared in Edinburgh and as it appeared on Tenerife. He was a great expert in spectroscopy. I'm going to skip past a lot of this. Very interested in the spectra of the zodiacal light, auroras, and showed that the zodiacal light was basically just reflected sunlight, contrary to opinions at the time. He also got very interested in the Great Pyramid and even had himself a pyramid-shaped tombstone. Now, I'm going to skip past a lot of this. McClure was involved in a great many things which probably didn't help his reductions much. And as the only scientist officially in the Cape, he was even held responsible for weather predictions, with the result that someone in a local paper drew him as a weather wizard. And his successor was the one who had to reduce all of McClure's data, which he did apparently in a very routine way. Nobody liked him very much. And Gill was extremely unimpressed with the way he did it. Stone also kept pigs on the grounds, or his wife did, which dug up the grounds. The main building was partly taken over by swarms of bees. And there in the dismal swamp, things were looking very old, worn down, and behind the times. But Gill was a watchmaker by trade and an enthusiastic amateur astronomer, and he was not going to tolerate any of this very long. When he tried to adjust the 7-inch refractor, he found that half a pint of water poured out, which gives you some idea of the state of the instrumentation. There was dust and old oil all over everything. And he was not allowed to get any new instrumentation, but he had bought a heliometer on his own account from Lord Lindsay. And he promptly started measuring parallaxes, which since he was an outstanding observer, ended up with parallaxes within 1/100th of a second of arc. He absolutely loved the heliometer, and he was brilliant at it. And he used it, among other things, to get an improved solar parallax by observing asteroids, Iris and Sappho, after he had talked the Admiralty into buying him a bigger heliometer. Now, we're going to skip over some of this because we've actually covered it already. I can't resist, though, showing you the picture of these Victorian workmen putting the telescope together, the 24-inch refractor. Gill had to strengthen the mounting with struts, as you can see in the right-hand picture, because Grubb had, as usual, not quite come up with a finished design, and the mount flexed much too much until Gill arranged things with a local railway yard. Spectroscopy became part of the standard at the Cape, and he hired women as computers who measured plates and so forth. He had trouble, however, keeping them because they offered better wages in the gold fields. And he came up with a radical state-of-the-art Meridian instrument that set the standard for decades and for a long time was the only principal source of southern star positions. Now, I'm going to stop about there. I'll just skip past his work on surveys and end with this slide.
Very much. I think we have time for one comment or question.
Okay.
Where can we get these slides? This far we cost.
Yes, well, I'll be happy to supply you with a copy of the slides if you want one.
Well, thank you very much. Our next speaker is Nikolai Samos from Sternberg Institute, I think, and he's going to talk about the Herschel family in South Africa.
So here, back, yes. Okay. Well, ladies and gentlemen, I'm not a historian of astronomy, and I'm here mainly because of my co-author, the Russia's most well-known historian of astronomy, Dr. Alina Yeremeyeva. I represent Institute of Astronomy and Sternberg Institute in Moscow, and also the Eurasian Astronomical Society as a co-chairman. And Yeremeyeva represents Sternberg Institute. And here's her daughter. She's 95 this year. And unfortunately, a trip to South Africa would have been too serious a job for her. So after being invited by Chris Sturken to prepare this presentation and supplying me with her materials, she told me as a co-author to go and present. And she even permitted me to, well, give my own accents and even disagree sometimes with her conclusions. You see here Dr. Yeremeeva with her book on history of astronomy, the book in Russian, and on August 23rd, he will go to the Caucasus, to the All-Russian Astronomical Conference. So this lady still travels, though not to South Africa, unfortunately. Well, this session deals with the history of South African Astronomical Observatory. And my talk is not about this subject, but about her family. When discussing this with Chris, I got from him a message stating that Herschel, John Herschel, is connected with the South African Astronomical Observatory through Thomas McLeod, mentioned here several times already, a royal astronomer at the Cape of Good Hope. And actually, during John Herschel's stay in South Africa, McLeod participated in his observations. So the connection is very deep, actually. Well, since my talk is about Herschel's, I have to start with Frederick William Herschel, known in Germany as Friedrich Wilhelm Herschel. His life was between 1738 and 1822. And his sister, Caroline Lucretia Herschel, who lived a very long life for that time, you see. Here is a non-standard portrait of Caroline. A typical one will be later. Friedrich Herschel was born in Hanover on the 15th of November, 1738, and the family moved to England when he was 19. And he died at the age of 83 in 1922 and was buried in Slough, England. That's a location 32 kilometers to the west of Midtown London. And his younger sister Caroline joined him in England slightly later in 1772 and stayed in England till her brother's death. And then she returned home to Hanover. The talents of William Herschel were multi-sided. He was a talented musician, composer. He played quite a number of musical instruments. And for some time, his job was musical performances at a spa. And people would come and listen. But he became an amateur astronomer and since 1773 started observing. And he had to find an assistant, and his sister became his assistant. Not only assistant, she discovered several comets, and actually a very interesting fact is that she became the first woman in England to get a salary from the king for her astronomical activities. And the salary of the time was £50 per year. And An attempt to recalculate it into today's money gives something like 8,000, quite an amount for part-time work. Here's the traditional portrait. But of course, she was not always old. And at the time she helped her brother, she was robust and much younger. In this portrait, she's 78, and internet sources say she was only 130 centimeters tall. I don't know if to believe, but at any rate, she was of very small stature and worked with large telescopes. As for William Herschel's most famous discoveries, the greatest one is, of course, planet Uranus. He discovered it in 1781, and for this discovery, he got one of the highest rewards in English science, Copley Medal. Also, he discovered two satellites of this planet, Titan and Oberon. Both were discovered on the same night, on the 11th of January, 1787. Also, two satellites of Saturn, Enceladus, on 28th of August, 1789, and Mimas on the 17th of September, the same year. And you should understand here that the satellite names were not given by him. These names were invented by his son, John Herschel. Well, there are two pictures here. One is the satellite Enceladus, and the left one, well, it would definitely be a surprise for Herschel. It shows Uranus with rings. Of course, he had no idea that his planet would have rings. The most important results were obtained by William Herschel in the field of galactic astronomy. This is how he imagined our galaxy. It's an elongated stellar system with the sun in the center. In the equatorial plane, you see something like a hole, certainly due to extinction. He didn't know about it. This picture inspired my co-author greatly. In the slide you see now, he compares the nebula in the sky as imagined by William Herschel and Charles Messier, compared to the Vauquelin supergalaxy. This is from Yeremeyeva's book, Herschel's Universe. She also wrote such a book, published in Russian language. I brought this book to Chris, and Yeremeyeva just marked the page with this picture for him. Also, one of the important results by William Herschel was that he was the first to identify double stars. He discovered a lot of nebula and star clusters, more than 2,500 of such objects, and published 3 catalogs of such objects. And then he designed and built several reflecting telescopes of excellent quality. We have already had a picture of this telescope in our session. This is the so-called Herschel's 20-foot telescope. 20 feet is the tube length, and the mirror diameter is about 0.5 meter. And this is a reflecting telescope. You see a platform. And the observer, Caroline Herschel, a very low stature woman, had to be on that platform and look into this tube. It's really a very serious job. And now we come to the sun. Sir John Frederick William Herschel, who lived a life of 79 years. Also a very talented man, but in variance with his father, he had regular education and would claim high position in the society since his youth. He became the member of the Royal Society since the age of 20. It's something. In 1842, he got the title of the first baronet. He was the only child of William Herschel. He was born on the 7th of March, 1792 in Slough, and died on 11th of March, 1871 in Collingwood. That's the county of Kent in England. He worked in many fields, in astronomy, mathematics, chemistry, photography. An important achievement from today's point of view is that he introduced Julian days to astronomy. We use them and we don't always recognize that this is the idea of John Herschel. He was married to this beautiful woman, Margaret Brodie Stewart, and they fathered 12 children, 9 of them girls. And it is rather easy to find information about their kids. And several of them lived for more than 90 years. 90 years was an age of that time. And so they had very strong roots. John, as I have already said, was well educated and showed many talents in different fields of science. The most interesting thing in the context of what was told about astronomical photography today is that he had many talents related to photographic techniques. And he even invented his own method of photography called cyanotype process. He had experiments with color photography, though not quite successful. He couldn't fix the images. At the age of 24, that happened in the year 1816, John started to help his father with astronomical observations and actually becomes an astronomer. He was one of the founders of the Royal Astronomical Society. It was founded in 1820 and called at that time London Astronomical Society. Because the Royal Astronomical Society, it needed patronage of the king. And it happened in the year 1831. He was running for the position of the president of the society. As a candidate, he was considered a certain ones, so he didn't run actively and lost to one of the princes of that time. So he wasn't elected. I mentioned that his father, William Herschel, published catalogs of clusters and nebula, and John Herschel published General Catalog of Clusters and Nebula, the famous GC, year 1864. He added 2,307 new discoveries to those 2,500 clusters and nebula that had been discovered by his father. Now, in the year 1833, John Herschel takes his dad's 20-foot telescope and goes to Cape Colony, Cape Town. Here he establishes an excellently equipped private observatory and observes the southern sky till 1838. Unfortunately, I'm the first time in this city and I don't know where his observatory was. Maybe people who know Cape Town better will tell me. But having finished observations in 1838, he was reducing his data for 10 more years. And the result of his work was the book Results of Astronomical Observations made during the years 1934, 5, 6, 7, 8 at the Cape of Good Hope, being the completion of a telescopic survey of the whole surface of the visible heavens, commenced in 1825 by John F. W. Herschel, London, year 1847. Well, John's excellent observatory here attracted famous people, distinguished guests, passengers of sailboats anchored at Cape Town port. And he was a known figure. And as a known figure, he was a victim of mystification. There was a book published claiming that John Herschel is able to see animals and people on the moon with his large telescope. The moon was immediately translated into several languages, Russian among them. And it is known that the reaction of John was laughter. Well, how did he see the galaxy? He imagined our galaxy, and in his opinion, this was the universe, as a thin layer, indefinitely large in size. And the sun is not exactly at the central plane. Erroneously, he thought that it was to the south of the central plane, while actually it is slightly to the north. He described Magellanic Clouds and claimed quite correctly that they are comparable to the whole universe, to the galaxy, in their richness and variety of objects. And for me, it's interesting that the photograph of the small Magellanic Cloud to the right on the screen also contains the globular cluster 47 Tucanae. In fact, if I remember correctly, you can find another global cluster in the photograph, but I cannot show it now. Now, a very important achievement of John Herschel during his stay here was educational project. By the time, teachers were considered people of low level and like servants. And John developed a plan of educational system for the Cape Colony with doubling salaries and providing pensions. So I think South Africa must consider him as a person who did much for the level of education in this part of the world. Now, the point where I disagree with my co-author. Gary Mawa used to say that John discovered more variable stars than William. I'm an expert on variable stars, and I tried to check her claims. There were incorrect variable star names, and they are in her book. William Herschel actually discovered two very well-known variable stars. That's Mu Cephei, Herschel's garnet star. In the present-day classification, it's a red semi-regular supergiant variable. And Alpha Hercules, year 1795, type the same. As for John, Alpha Orionis, year 1836, same type. This is an interesting star of Flores White. Alpha Hydra, Alphard, 1837. I cannot count. It will be. I cannot count this star. It is only a suspected variable in the catalogs today. And SV4496. So this discovery of John was probably erroneous. And Eta Carina, after the year 1837, current type S. Doradus. Actually, it was not a discovery, it was a confirmation. And Herschel observed an unprecedented brightening of the stars, the so-called great eruption. Thus, despite claims of Jeremiah, John doesn't win the competition. As for Alpha Orionis, in the year 2020, it underwent an unprecedentedly deep minimum of brightness. These are AVSO data V-band. It was so deep that we had to quickly introduce a correction into the general catalog of variable stars. Usually I don't like to do that, but this was a very, very extreme case. At the time, 2020, I happened to be at Tenerife Island. There, the constellation is on its back, and you can see Alpha and Beta Orionis approximately the same altitude and compare them directly. I made an estimate and sent it as a visual estimate to the AVSO, but I was too pessimistic. No one saw it that faint as I. And this is the AVSO visual light curve of Eta Carinae since Herschel's time. And mainly these are visual estimates. And you see here the famous great eruption observed by John Herschel. And then the final thing I want to tell you, as an excellent teacher and popular science writer, John Herschel authored several popular science books and textbooks in astronomy. During his stay in South Africa, he wrote the book Treatise in Astronomy. And in 1849, he finished the two-volume book Outlines of Astronomy. Its first volume was published earlier. It was actually a universal textbook in astronomy. And it was published in Russian as early as in 1838, translated by Navy Lieutenant, in future Rear Admiral, Paul Krusenstern. And Paul Krusenstern is the son of the famous admiral whom in the West you know as Adam Johann von Krusenstern. And in Russia, we call him Ivan Fyodorovich Krusenstern. And he's very well known as a Russian admiral with a monument at the Neva River in St. Petersburg. You can come and see. Well, that's all. In this slide, I wanted to write in several languages, but I didn't decide which of the local ones to use, and decided that maybe using Afrikaans is a bad idea. That's all.
We have any comments or questions, please? We have some time. Yes, over there.
Many thanks for your interesting talk. I have two questions by my curiosity. The first, you mentioned that the observatory of Herschel in Cape Colony, the location is not known. Okay. What? Okay. Yeah, actually, during my stay in Cape Town, I wish to visit this place if possible. Is his for the location of his house, is it known? Okay. 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 If anybody knows, please kindly let me know.
His house is gone. I mean, it's yeah, but in his will, actually he had a big property. When he left, he sold it to somebody who developed and housed it. So it was, but he bought he kept part of it, very small piece of land, eternally, and that is known. And there is an obelisk on it. It's a monument. It's a national monument. I'm going to show it tomorrow in my talk, and you can easily go there, but it's surrounded by a school. Yeah, but if you ask kindly, then the director will let you in and show you the place. Yeah, but the house itself is not existent anymore.
Yes, he's saying that the house has been demolished. That was around about 1950, but the monument exists on the exact position of his telescope, and it's in the grounds of the Grove School in Claremont. Well, you can see it through the fence of the school. I don't know if you can go right up to it. You probably have to get special permission for that. You can certainly see it.
Right. I definitely wish to take this opportunity. And the second question, you showed with some right curves from the time of Herschel. And how do you calibrate Herschel's observations? Are they directly compatible with the modern variable star observations?
Probably one right curve that contains data points from Herschel's time.
Okay.
That's the light curve of Eta Carinae.
Yeah.
And well, the amplitude is so long
Yeah.
that any mistakes are not obvious in this slide.
Okay.
Or
Yeah.
even in much simpler cases like T coronavirus, people are now expecting the new outburst, and they argue how bright it was on previous occasions. People normally say second magnitude, but some people say that actually it was third magnitude. And thank you for asking about light curves. I forgot one thing to say. That is, people predict that Alpha Orionis will explode very, very soon. I don't quite believe it. My position here is, well, it will explode soon. But how soon? One day or 1,000 years? I don't know. And no one knows. But we must just keep in mind that this discovery of John is to be followed very carefully. And imagine the constellation of Orion without Alpha. It will be something.
Spasiba.
Any more comments, please? David?
Just that Herschel's estimates of the brightness of Eta Carinae are probably not too bad. You can read about this in the letters exchanged between Herschel and Maclear. They compare it basically to the brightness of other bright stars in the southern sky.
Yeah.
And the maximum is estimated basically with reference to Canopus.
Yeah, that's just the magnitude is close, more or less. I'm sure they could do it. One more question, please.
About the achievements of John Herschel in terms of binary stars. So he also observed, I mean, I don't know how many, but can you tell us more about his binary star catalogs?
Wow, super. And that's all. I especially studied the situations in Blu-ray stuff.
Okay.
But in the field of binary stars, well, I know that he made a very important difference.
I think he actually solved one of the first binary stars for masses, and that was quite important. Yeah. It could be Alpha Centauri. I just want to mention we found a hotel door ticket in case anybody's lost it. So, any more questions or comments? Well, I thank you very much for your presentation. And I thank all the other people who made presentations today. So let's give a clap to them. could say thank you very much to our organizer. He has done a wonderful job of putting all this together. It's Christian, of course.